Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
And this is the podcast where we explore theories that we think may change the world one day. And we are turning our attention to fusion today. And in general, fusion is this process which physics tells us requires extraordinary temperatures and pressures that you essentially only would find at the heart of a star. Maybe you can promote fusion inside of some enormous laboratory instrument like these giant magnetic tokamaks where you can find plasmas and emulate what people expect to see at the heart of stars. But perhaps there's a different road to fusion. Perhaps these same processes can be seen at ambient room temperatures. And with us today, we have Dr. Lawrence Forsley, who is a PI at NASA's Glenn Research Center, where he has been developing the idea of lattice confined fusion, which is a pretty simple project on its face, where instead of having these really high energy fuels that are trying to bash into each other inside of a plasma, you essentially impregnate a metal with the same fuel, these deuterium fuel sources, and you use the lattice of the metal to do the work that the magnets are doing inside of these very big tokamak reactors.
It's a really wild conversation because the idea of room temperature fusion is something that has been the butt of pretty much every scientific joke and crackpot dismissal for, I don't know, maybe like 70 years since the 1950s, where people have been saying that they've discovered cold fusion. There's been huge debate inside the community about whether or not this is actually happening. And for decades, it was completely sidelined. Nobody believed that it was possible. And it turns out that in the background, Forsley and all of his colleagues have been working continuously on trying to figure out what anomalous things are happening inside of these palladium lattices that are doped with deuterium atoms. And so we go through the entire history of the field from, the Fleischmann and Pons paper all the way to the present day, where there's companies that are working on devices that leverage lattice confined fusion in order to be able to produce medical isotopes for hospitals all around the world. It's a really cool story because at the heart of it is this scientific black box, right? So stars are supposed to be fusing, and yet we have room temperature fusion that has sort of a mechanism associated with it. There's this thing called electron screening that we talk a lot about. But when you really get down to the moment of fusion, what happens when you take these two deuteriums and you squeeze them together? Like the science of what's actually happening there, and the mechanism is still missing. And we think that it has really profound implications, not just for the development of more fusion technologies on Earth, but for our understanding of astrophysics as well. And it seems that Forsley agrees.
Yeah, there's definitely something really interesting happening at the moment of star formation. How do you actually get the fire going in the first place? And so a lot of these principles may be transferable to some mysteries at that moment of stellar inception as well. And we play with that a bit. I think you guys are going to love this conversation.
But before we get there, there's two things that I have to ask you for in one case and remind you of in the second case. The first is that this is a podcast that is purely supported by patron donations. That means that you, the listeners, are the people that make this possible. We don't want to sell you stuff. We don't want to have sponsorships. We don't want to be shilling pills and rugs and mugs. We want to believe that it is possible to create something that is so useful and so meaningful for people that the people who enjoy it support us. And so come over to patreon.com/demystifysci. You can keep us going for 75 cents a week, which I know that it's dark economic times for pretty much everybody, but if you can spare 75 cents a week, you will make it possible not just for you to enjoy this podcast, but for everybody else in the world, and will directly contribute to making the world a slightly brighter, more legible place.
If you are already supporting the podcast, thank you so much. You are the lifeblood of this operation.
Absolutely. I agree with that.
Secondly, if you have an idea that you think is podcast worthy and you need to share it with the world, maybe you have a theory of how something works that people have been messing up for ages or no one's ever even considered before, come out and share it. We have this new segment called Paradigm Drift. We record it once a month. Next one is on August 4th, 7 p.m. Pacific. And you're welcome to sign up, put your name in the hat, and we will randomly draw folks out and give them a minute to present their idea. So if you can convince us that there's something interesting in a minute, maybe we'll talk to you for 10 minutes or so afterwards and try to, figure out where this came from and so forth. But if it's really cool, we'll invite you back and you won't have to sign up next time. And if that's still really cool, who knows, maybe you will end up sitting here on this podcast as well.
Sharing your ideas in long form with the entire world. I'd say that's a pretty cool prize.
With that, enjoy the conversation with Lawrence Forsley, and we'll see you next time.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
You're a guy who's been looking at fusion for a very long time, and we're super excited to sit down with somebody who's been studying it so intensely for so long. And I think that we've had a few conversations around fusion, but nothing directly about it. And the one thing that's always on the tip of our mind, since we, have been watching this unfold from the outside for our entire lives, is it always seems like fusion is 10 years away. Like we're going to have fusion-powered cars 10 years from now. Always. It's always 10 years away. And I would love to just understand what is there a consistent hang up? Like what's going wrong? Why does this always seem like it's within reach, but it never is? Yeah.
Yeah. So I suppose the first thing is, most people have heard of fission. Some have heard of fusion. Fission is breaking large atoms into small pieces. That's a fission reactor. Fusion is taking small pieces and sticking them together into larger pieces. And it turns out that those small pieces have positive charges and don't want to stick. So the conventional way of doing it is to squeeze them together real hard against their will. That's inertial confinement fusion. Or try to get them really hot and hold them in a magnetic field, and that's magnetic fusion. And both of these are fraught with major difficulties. And the joke used to be fusion is 20 years off and always will be. I didn't know that it dropped to 10.
I pulled up this headline. I forget. It was on the cover of some magazine, like
in the 1970s, I think, wasn't it?
I think it was 1980 or 1982. But it said, fusion by the 1990s. And, I guess by like different measures, right? Like there's ways of measuring this. If there's some gains, do you actually get fusion reactions? Okay, fair enough. But I think that in the public's mind, like it's right around the corner. We'll just have endless, clean, cheap power for all of our gadgets. And it just doesn't seem to... Did it ever look that way to you when you were first getting involved with this? Okay.
No, I mean, this August, I will have been involved with fusion for 50 years.
Wow.
And all I can say is the amount of money spent and the cleverness that has been used hasn't really gotten us by those means any closer.
And what's the internal state of the scientists that are working on it? Is there just a sense of utter doom and dejection, or are there true believers?
Oh, quite the opposite.
I see.
No, quite the opposite. When I began this in the late 70s, I was working in laser fusion, which is inertial confinement. You have a small glass ball about a millimeter or smaller in diameter, and you use multiple lasers to blow away the outside to compress the inside. And we used to comment that we are getting closer to understanding what's going on, but there's always this X factor. We called it the X instability. So the plasma would find a new way to leak out. And the same thing happens with the tokamaks. If you've got something that's 10 times hotter than the center of the sun, and you can't allow it to touch the walls because they'll instantly vaporize, so you've got a very strong magnetic field holding it. Great. Now, it turns out there's a limit to how much material you can put into the plasma. It's actually called the Greenwald instability. And if you wrap on your desk, all right, your desk's atoms are at a density of about 10 to the 23rd atoms per cubic centimeter. That's pretty dense. Unfortunately, the plasma can't go over about 1/1000th of that before it becomes unstable. So right off the bat, you got to make your tokamaks really big so that you have enough fuel to get enough reactions to make something that works right. That's kind of a limiting factor, but everyone's pushing it. And the latest round over the last 5 years, with a lot of push from the Department of Energy, what's called ARPA-E, has put now close to $90 million into a lot of small startups. And one of the major things they're doing is to come up with better magnets, better superconducting magnets, make the strength of the field stronger, make the tokamaks smaller. But unfortunately, I think the Greenwald limit still says, we're not doing that today. If you do, the plasma will squeeze out. So the thing about it is like having a balloon, and you're trying to take the balloon filled with gas, you're squeezing it down, and some of the balloon squeezes out between your fingers, and some squeezes out the other way. And no matter how hard you squeeze it, at some point the balloon is likely to break through and hit something, or just break entirely. That's not a good model.
So is it partially because the magnetic fields that are being used for confinement are stable? Because like immediately as you say that, I'm like, okay, so if you have your hands in there, they're trying to squeeze the balloon, obviously that's not going to work. But then if you were able to take your hands and then rotate them very quickly and compress as you're squeezing, then perhaps you wouldn't run into this problem.
Very good point. And there is a clever startup that comes out of an ARPA-E and I believe also an NSF program that's called centrifugal mirror fusion. And so what they do is get the plasma rotating very rapidly inside of a device whose two ends keep it from going out the ends, and the center is rotating quickly to get around the problem you just described. And they have high hopes. I know, actually, I've met both and know one of the CTO very well on that. And they're based out of the University of Maryland.
But so when you say high hopes, there's a big headline, I think probably 2 years ago at this point, where it was like, finally, fusion has achieved net power gain. And everybody from Neil deGrasse Tyson to Good Morning America was just talking about the fact that like fusion has arrived finally. And then you get the internet sleuths who start to look into it and realize that we're still, I think maybe 2 orders of magnitude more power, 3 orders of magnitude, 4 in the facility and in the production. And so the gain from the reaction itself is still minuscule relative to the full infrastructure. And so when you say that they're optimistic, are they optimistic on 4 orders of magnitude optimism, or are they optimistic in the sense that they have their $90 million of ARPA-E money and they're
No,
sitting pretty?
it really has nothing to do with that, because this was the Lawrence Livermore National Ignition Facility. And this was predicated on work by John Knuckles going all the way back to the 70s, who kind of came up with, among other things, canonically, how would you have to do this? And so some of the things at the time were you had to deposit 10 megajoules of energy onto the target. You had to do it 10 times a second, and you better get gain of at least 10 times that out. Now, there's several problems with this. So we'll start with the Livermore results from a few years ago. First of all, as you correctly noted, they described the amount of laser energy dropped on the target versus the fusion energy coming out. They got more out than they dropped on it, but that did not take into account the amount of energy required to charge the capacitor banks that discharge the laser. That's where the factor of 100 to 1,000 or more comes in. So if you want to measure wall power to fusion output, you're way off. The second problem with the approach is they're doing what's called deuterium-tritium fusion. So you have hydrogen all by itself, just a single proton. You have deuterium, hydrogen, atom, proton with a neutron, and it's not radioactive. And then you've got tritium, which is the hydrogen proton, but with 2 neutrons and is radioactive with slightly more than 12-year half-life. It turns out what we call the cross-section or the capability to fuse DT is 100 times greater than to fuse DD. So you go for the easiest mark, and the easiest mark is DT fusion. The second problem with this is 2/3 of the energy from the reaction goes off in very fast neutrons. They don't want to stop. They want to just keep going. They want to interact with the walls of your chamber and make it radioactive, or knock atoms out, or displace them, as we call it. And then the third problem you've got here is that laser is run a few times a week, not 10 times a second.
Mm.
So you've got to ask yourself, how do we get from running a couple times a week to a couple times a day to 10 times a second? And this is a major problem, because depending on what the laser you're using is, you will destroy it if you try to run fast. You've got to let it cool down.
Yeah, I was going to ask. It's not the fact that they have to rebuild the chamber every time because it's
No,
so
the
strength.
chamber's fine until it gets radioactive. But you have a bigger problem with the tritium. Where does the tritium come from? So for many years, the Department of Energy would publish the status of fusion research. And I used to go through these, and there would be 10, 20 pages devoted to instrumentation, to current results in a variety of inertial confinement or magnetic confinement fusion. And they always kind of glossed over the tritium problem. And the problem is, your tritium currently is made in a fission reactor. So you can use, say, lithium-6 with thermal neutrons from a reactor, and you can breed tritium. Now, if you think about a fusion reactor, it's supposed to do without fission reactors, yet the fission reactors make your fuel. You got to ask yourself, what is the fuel cycle here? What am I replacing? The second problem, which has been recognized for a long time, is how do you increase the tritium output within the reactor? You're burning it. You've got all of these neutrons going off. Can you do something to use them to convert into more tritium? One of the clever ideas that came up with back in the 70s, early 80s by the University of Wisconsin is they called it the lithium waterfall. So you have a chamber like NIF, and you have molten lithium running down the sides.
Wow.
And the neutrons get captured by the lithium. The problem there is you've got 2 kinds of lithium isotopes. One is a little bit heavier than the other. Lithium-6, lithium-7. Lithium-7 has an extra neutron. If you've got thermal neutrons and you hit the lithium-6, you can make tritium. So you can make your fuel. But the neutrons coming out of a fusion reaction aren't slow. They're very fast. So you better put more lithium-7 in. But not all of it gets converted into tritium. So some of the neutrons keep on going. So here, if you're burning tritium, and every time you burn it, you're producing neutrons, you've got to save all the neutrons to make more tritium. And that seems to be a little bit off. So another group at the Joint European Torus up in Great Britain, at one point lined the inside of their tokamak with beryllium. Now, beryllium, when it gets hit with a fast neutron, will produce 2 fast neutrons. So it's a neutron multiplier. The problem there is that beryliosis is when you get beryllium oxide, and even though you're in a pressure chamber, rather in a vacuum chamber, eventually you've got to have people work on the chamber. As soon as they go in, you have oxygen, it reacts, and beryliosis is a terrible way to die. So anybody working on the inside of jet after they started using tritium and beryllium had to wear bunny suits with full respirators and everything. This did not seem good. So these are some of the issues that have come up in trying to make the fuel.
Are you aware of any precedent for this kind of technological iteration where people are just bashing their heads against the wall trying to improve some design that just seems to be, maybe fundamentally the wrong approach or something like that? Is there anything in the history of technical inventions that follows this form?
Two come to mind: flight and
Hmm.
semiconductors.
Ah, flight. Yeah, flight's a great one. I could see that. But yeah,
You
tell me
know,
about. I don't know about semiconductors either. Let's talk about this.
about which one?
Both of them. Yeah.
Okay, well, in terms of flight, I think the first recognized in the West, though not in the East, was the two brothers in France in the 18th century who had a lighter than air balloon and went up and looked around, looked down on Paris, and had a great old time. And then we've had a number of people going all the way back to Icarus, you know, building wings like a bird and falling out of the sky. And we've had a number of people associated with the Smithsonian in the latter part of the 19th century trying to do this, but it wasn't until Wilbur and Orville Wright built a wind tunnel, figured out what the real issue was, which turns out was three-axis control. No one had figured that out, and then they flew back in 1907.
Hmm.
So that's one example.
I guess that feels somehow fundamentally different because the amount of effort that was being directed at flight seems like it was a lot less than
That's
the
true.
amount of effort that has gone into fusion research.
Well, so ask yourself, why has so much work gone into fusion? And a lot of it has to do with the weapons programs.
Mm,
So there's a lot of money to understand how to make thermonuclear weapons.
this is true.
You would
And
think.
it has a flip side, which is we could, quote, commercialize it.
Yeah,
And
you
if
would
you
think
look
the
at
military would
number
have
of,
been driving a lot of the flight research at that point.
I'm sorry?
I would have thought that the military would have been driving a lot of the flight research as well in the early days.
Not until World War I came along. One of the classic examples is when, and I think it was Orville took a army captain up over the field, which one was it, in Virginia, and he fell out and died
Oh, wow.
because the army did not believe that this was possible, that humans could fly. And they then had the terrible problem of figuring out, how did he fall out of the sky? Because planes are impossible. We all know that.
So
World War I is what really put flight on the map, initially for reconnaissance, and then the rest is history.
how did he fall out? Do you know?
Yeah, he was excited and he leaned to look over at what was there down at Fort Myers and leaned a little too far. And he's in a completely open cockpit in a wooden frame plane.
The
Doesn't-
self-preservation instinct, I think, was overshadowed by the awe of the experience.
Oh, he was so excited.
And Orville Wright just came back down and was like, all right, moving on. We'll just keep building
I
planes.
don't remember whether it was Orville or Wilbur that was flying, but I'm sure he didn't feel very good about what just happened.
Okay, so they needed a proof of concept before the institutions were willing to pour money into this thing into flight.
No, not one. They
Yeah.
needed dozens. I mean, at one point, they were demonstrating in France because the US wasn't paying attention.
Interesting.
Here's the thing. In all of these areas, it is the common knowledge that A is impossible.
Sure.
This goes back to the semiconductors. All right. The development of the transistor, the first transistor was demonstrated it's not demonstrated, it was presented at a conference in I think the late 1940s, and vacuum tubes were triumphant. Everybody knew they worked. This little funny gadget didn't make any sense at all. And as a consequence, it was rendered so unimportant that they didn't even bother to put the paper into the conference proceedings.
Wow.
Yeah.
This was
Now,
the first point contact transistor?
Yes, exactly.
I mean, I
Now,
can understand why people dismissed it because have you ever seen a picture of it? It looks so
oh, it-
doofy. It's
it's
just like
lovely. It's
loose
homemade.
wires and this like weird hanging triangle that's touching some substrate. And you look at it and you're like, that's not going to do anything.
Do you know about the cat whisker germanium detector for radio?
No.
Yeah, I actually had one of those as a kid. The very first, you would pick your station by having this piece of germanium crystal, and you'd run the wire over it to try to pick the station up. All right,
Wow.
that goes all the way back probably to Armstrong in the 1920s, coming up with super heterodyne radio and things like that. But if you look at the traversal for transistors, it was almost 20 years long. It was material science. And before we were able to do it on a large scale, we actually got into just about the 1960s because it was a materials problem that no one recognized.
And there was
So
also a
if
lot
you've
of
got,
investment into vacuum tube technology, right? Like the ENIAC, the EDVAC, these are huge machines that the government has put an enormous amount of money into. There's just crews of people that are working them. And so it seems like there's also a hysteresis when it comes to having a technology that works that you've spent decades developing that now you have to switch over to something new and then what, throw the thing away? Like
oh, no, it's worse. And I have personal, let's just say, I personally was involved with this. University of Rochester, we developed what at the time, which is probably in the early 80s, the world's fastest oscilloscope by probably a factor of 10 or 100. And the university licensed it to Princeton Applied Research. We thought, we'll make a bundle. This will subvert all of the other oscilloscopes. What did PAR do before? And I think they were in the process of being bought out by EG&G. They sat on it.
Hmm.
The university had inexplicably given them exclusive rights with no hooks or anything, and they just sat on it because they had an investment in a variety of oscilloscopes. And the last thing in the world they want to do is to render those useless, and all the money put into it, all the marketing put into it, et cetera, et cetera, et cetera.
And so you think that transistors were held back both by some amount of financial investment into previous technologies, but also the fact that the material science took a long time to work out for it to be something that was.
I think it was all material science. It was difficult to get good yield. It was very difficult as we started going into laying them down. Fairchild did this, laying them down, and then the Manhattan layout. That oh heavens, what's his name? Keep thinking it's Conrad. Two of them wrote a book on Manhattan layout. That became the guiding book in the mid-late 70s forward on how to design integrated circuits. And Fairchild came up with the first one. But all of these had the material science problem that we didn't recognize. Parts per million or parts per a tenth of a million would in fact corrupt your device. So as the line width gets smaller, everything changes, right down to today's processors.
So back to the fusion question. Was the proof of concept these thermonuclear weapons? Is that why these governments are willing to put a lot of money into this project that seemed to be ever receding in terms of its, promise?
Yeah, I think so. If you look at the, let's see now, I'm trying to remember what the ruling was. We all agreed that there were a whole series of treaties signed that the various countries that were signatories would not use an atomic bomb to detonate a fusion device. Now, what that did is it left open, were there other ways you could detonate a fusion device? So you could use lasers, you could use particle beams, and eventually going forward, you've got General Fusion up in Vancouver that are using molten lead with these sledgehammers coming in to compress this thing. All these other things are possible. Just don't use an atomic bomb to do it, a fission bomb.
And what's so advantageous in terms of killing power for a fusion bomb versus a fission bomb?
you can scale it by beginning with probably a factor of 10, and the largest fusion reaction on Earth was called the Zara, which was or Bomba. It's a Soviet bomb that was, I think, 56 megatons that was set off in the plains of, I believe, Kazakhstan.
And did it have
And it was
fissile elements as well?
well, it had a small, it had a fissile element to set off the fusion element. It was actually a fission, fusion, fission. I think possibly another stage. It was a 3-stage device.
So they weren't worried about the treaty.
Oh, they could care less. I think this was actually before the treaty. This was
Okay,
probably late 50s, early 60s.
interesting.
And
So
we had a number of treaties. You don't test these things underwater, on the ground, in space, all of that after we had done all of those things.
Everybody's like, this is a bad idea. We should we should take a step back.
was this empirically determined? Like, I'm trying to understand why it scales so neatly. Like, why is fusion so promising in these initial days? Like, how did they figure this out? Was it theoretically determined before it was implemented? Were people searching for fusion weapons, or did they just kind of realize that this was a multiplier?
No, you got a couple different groups. You got one group that was very interested in fusion weapons because if you could use less fissile material, which is expensive to make, U-235, highly enriched, or plutonium, which is hard to extract, and you can get more bang for the buck because deuterium is cheap and tritium is relatively cheap. And there's a clever way to make the tritium in situ using lithium deuteride. All of this is now in the open. There was actually an article published in the magazine called The Progressive that kind of cracked open how all of this worked. And immediately the US government tried to get all the copies off the street. This is long before there was internet. You're stuck with fax machines and telephones.
Wow. Yeah,
But
that must have been quite a
that was a
police
major
job.
driver. But what came out of that was the realization that if you didn't have to use uranium, you could build a pure fusion power plant. That could be a real gain. And we know the sun works. Astrophysics is real. We just have to figure out how to do it. The problem is that they do it using gravity, and we can't do that down here.
I want to get back to the stars later because I am very interested in the application of fusion ideas and the way that evolved in astrophysics too. But I still want to understand how this translated into these energy projects here. So people, they believed that it could be done because they're seeing this in thermonuclear weapons, and now they're trying to apply these same ideas to generators, essentially.
So one of the ways there was a branching. Sakharov is the one that with TAM invented the tokamak, which became kind of the model child because early on they got really good results, both in terms of confining a plasma first in Novosibirsk in Russia and then here in the States and in France. And it looked like this was doable. If you could make the magnetic field stronger, and eventually it became superconductors, if you could make it big enough, all of these things together, it looked like there was a path, and potentially initially a linear path to power out for power in that might become exponential if you got the thing to a certain size. So everybody pursued that, and it looked good.
So something that's a little bit low tech about nuclear power in general for me is the fact that what we're basically doing, even with fission plants, is just boiling water and running a turbine. Is that really the best case scenario for nuclear power?
Probably not.
What is like in an ideal world? Because the first time that I heard about nuclear power, I thought for sure that there was some kind of like weird unknown mechanism by which we were deriving electricity. I'm like 10 years old. I actually visited the National Ignition Facility on a class trip. And
Excellent.
but obviously there's not a grand context that a 10-year-old gets for what this really means. And so for many, many years afterwards, I had this impression of there just being crazy mechanisms at play where there's just like a giant plug that's somewhere plugged into the nuclear reactor and then just electricity comes out. But that's obviously not the case. That's the cooling towers contain turbines, the turbines spin, and it generates electric power the same way that everything
Well,
else does, except for the
actually,
fact that the steam is generated differently.
the cooling towers serve a slightly different function.
Hmm.
2/3 of the energy from almost any of these reactions, whether it's coal or nuclear fission or nuclear fusion, if you go that route, comes out as waste heat. You got the Carnot efficiency, so you can't really, even with using various multi-cycles, you can't really break 40 or 45%, which means you got to dump more than half the heat that you went all of that trouble to make.
Wow.
There is a system which I was involved in called the Mirror Fusion Test Facility at Livermore, which was coming along at the same time Shiva, which then begat NIF, was being built. And the idea is that you have a superconducting tube to hold your plasma, and on each end, you've got magnetic mirrors. Now, the problem is there is no way to couple the cylindrical magnetic field here to these complex magnetic fields there. And so the plasma is always leaking out. One of the things they recognized was they wouldn't be able to keep all of the charged particles made in the fusion reaction. You want to bounce them back in to keep the plasma hot. But what you could do, and which they did do, is they put in what are called charge screens. And so what would happen is you'd let these multi-MeV alpha particles from the fusion reaction interact by passing through the charge screen, induce an electric current. So now you've got a way to produce power from a fusion reaction without using steam. Now, it was never intended for that. It was intended to try to make the power budget to run all these magnets not so formidable. But the flip side is if you can make a small version of one, you could potentially take advantage of the kinetic energy of the charged particles, slow them down, induce a field, get the power out.
But obviously there's a problem with these, which is the fact that they're constantly irradiating everything.
Yes, it is a small problem. That's why you don't want to use DT.
Same problem
And
for fission, I suppose.
The problem is actually worse. Most of the efforts, and I'm in the process of writing a paper on this because this has become, along with a few other things in hot fusion, become very disturbing. One of the ways in which you increase the current carrying capacity of a type 2 superconducting magnet, which is typically a ceramic like BCCO, those the chemical name of it, or YBCO, is you can put it into a fast neutron field and you can knock atoms out, and that becomes a place for what's called flux pinning. So you can increase the amount of flux you can have in there, hence the current carrying capacity, hence the magnetic field, by using neutrons. Now, wait a minute. If I have superconducting magnets surrounding my fusion reactor, which is emitting lots of fast neutrons, how long is it going to run before the following happens? I start getting neutron impacts displacing atoms. I increase the flux carrying of that portion, not the whole thing, but that portion, which means the magnetic field associated with that portion becomes different than other portions. Now I've introduced an instability in the overall plasma because it's being confined by a magnetic field that is no longer as uniform as it once was. And then the problem gets worse because if you keep running, eventually you break things like the Josephson junctions between grains and you quench the field there. That's a really bad idea.
What is the Josephson junction? We've come across it before, but I don't remember.
A friend of mine, Brian Josephson, got the Nobel Prize for work he did as a graduate student at Cambridge University, Trinity College. It is a way in which you can have a junction and you can essentially apply a current and you can interact with it with a magnetic field and you can stop it and you can play with it and there's a frequency associated with it. It's actually a very brilliant paper that he wrote. And I think he was still a graduate student when he wrote it. I think there are only two people, he and what's her name, up in Canada, who have gotten Nobel Prizes later in their life for work they did as graduate students.
That's pretty incredible. And so basically this is just some thing that happens inside of these type 2 superconductors, and then when you break it, it
Well,
invalidates the
you're
magnetic field
losing the
that's built?
ability to have current in there by damage. And
Yes.
so now that portion becomes quenched. This was actually a problem we had with what was called MFTFB at Livermore back in the 80s,
What's MFTFB?
Mirror Fusion Test Facility.
Mm.
I had worked on the diagnostic side of its predecessor, TMXU, and then they built MFTF, and this program had a lot of problems. One of the problems being that the mirrors on the ends became as large as Tokamaks.
Wow.
So, it seemed from an engineering perspective, if you want to get more gain, more power out, just make this superconducting solenoid longer. All right, all the fusion's happening in there, but you got to keep the particles from escaping, so you've got to put a mirror on each end. And the mirrors consist of superconducting magnets the size of a 3-story house. And in center, there's a well, and that causes to push the alphas that are heating up the plasma back into the tube. But we have what we used to call the velocity loss cone. Because these things are sitting in there, they're not confined to going back and forth linearly. They spin around, and then they can spin right out, and that's the end of your mirror. It just leaves.
Okay, so actually, as you're talking about mirrors, I'm thinking about because something that I was thinking about earlier was, well, okay, so if one of the problems is the fact that the fusion products are constantly damaging the substance of the container. Generally, when you think about a mirror, you think about something that can interact with electromagnetic radiation in a way that it is not destroyed. Is that
Yep.
also the case for these mirrors, that when they're working properly, they're actually not being destroyed in the process of reflection?
Well, the reason is that they're not solid materials. They're plasmas in their own right. And they have to be, because you can't have a solid material that can get hit by a 6 million electron volt alpha particle and still be there.
I see.
So this is why you're using a combination of magnetic fields and electrostatic forces to try to keep things where they're supposed to be. But that turns out that doesn't work well.
So, like, in this sense, it's not mirror in the sense like the one that's in the bathroom. It's mirror in the sense of having its own, it's like creating its own plasma, and then the plasma
Yes,
serves as the
each
surface
end
to
has
bounce.
its own little plasma. That's right.
That's wild. Okay. And so, is there a material that's capable of reflecting radiation without being affected by it?
Well, you can reflect neutrons if they're really ultra cold.
How do you make ultra cold neutrons?
Carefully.
Alright.
In a very cold
I mean,
room.
what you end up doing is you take a neutron beam. You have the problem that neutrons do not experience electromagnetic force for the most part. They do have a magnetic moment. Um, and you can essentially allow them to bounce off of things, and some will escape, but some don't. And so you can produce kind of a cold neutron trap. And we talk about a thermal neutron. And you say, well, what's a thermal neutron? It has an energy, funny units, EV, 0.025 electron volts. That neutron is still traveling about 2,000 kilometers an hour. It's not really all that slow. A cold neutron is about 100 times slower than that, and you can trap them for a period of time. And you can use them for various things. Like I think Yale University has used them for a gravity well trap to measure whether or not we can measure the difference between the gravitational potential on Earth versus, say, on the second floor of the building. And turns out you can. So there's a lot of interesting places that this all kind of comes together. But in this case of fusion, it doesn't do you any good whatsoever.
Interesting.
All right, so there's all these standard problems amassing with the stability of the confined plasma, interactions with the chamber walls, and it seems like you are studying a very different approach right now. At least this is why we reached out to you to talk to you about this lattice confined fusion approach.
Right.
Before we get to that, though, I want to get your take on
Cold
other
fusion.
yeah, basically other people's. So
Oh no, she said the bad word.
well, I was gonna tee it up a little smoother, but you took the win.
Shiloh was like, "You can't say cold fusion during the podcast. You're gonna spook him." And so hopefully it didn't spook him too hard.
You can say it. I mean, let's put it this way. When the announcement came out in 1989, and I personally knew Martin Fleischmann, I did not know Stan Pons. In 89, I had left the University of Rochester, but I had been in fusion, hot fusion in Germany on a tokamak. I'd been with Livermore on MFTF. I had been doing laser fusion at Rochester. And I saw this and I said, this is complete bunk. And then about a year and a half later,
why did you think that? Wait, you just thought that was your first thought?
Yes.
Okay. Why?
This is impossible.
Yeah.
I come from the hot fusion community. This cannot possibly be.
Was it just because it violated everything you understood about the basic principles of fusion?
Yeah, there's a Coulomb barrier. You know, if it's like taking two magnets, and you can take the south pole of one and the north pole of the other. They're very happy. But if you try to put two south poles together, that's not going to work. You got to really work at it. We've worked with some magnets here that are so strong that when they get stuck together, you run the risk of taking off the tip of your finger when they snap.
Yeah.
But I took a visiting scientist position with the chemical engineering department at the University of Rochester, and they had been doing a series of experiments that were cold fusion, and some of them would later not be replicated for probably 20 years, but showed really odd results. And that was Jacob Journet. And so I worked with him. What was even funnier is the lab we had in chemical engineering was kitty corner from a lab and office by John Heisinger. John was over in Hutchison Hall. He was also my undergraduate inorganic chemistry professor, so I knew John personally, unfortunately. Wow. But he could see what we were doing. And we borrowed a calorimeter, device for measuring heat, from a colleague at Case Western University. His last name is Landau. And in doing one of the experiments, Jacob turned the power off before going home one night and then flicked it back on again. And when I came in the next morning, this plastic calorimeters where the screws held the top on was cracked. And I had a recording being taken every 10 seconds of the temperature differential between the outside and the inside. And it had shot up to 110 degrees Celsius, way above the boiling point of water. And then it exponentially decayed down. And so when I took the whole thing apart, we had vaporized the cathode, which was a piece of palladium metal. I thought, well, this kind of changes everything. So I reported this at a conference at MIT, I think in January of 91. Then what
happened inside the calorimeter? You said that he turned the power off and then he flicked it back on. Like, what was the thing that happened?
Well, so this is not well understood. I know of at least three other cases where this has happened. My suspicion is the following. You have a piece of metal that you've loaded electrolytically to very, very high density of deuterium, exceeding, pushing towards 1 deuterium for every palladium atom. It causes the palladium to expand. Usually it causes it to crack. But as a consequence of this, you now force everyone very close to one another. Now, what I didn't know then and didn't really know until about, 5-10 years ago, is there's an electron screening potential in here, and we've written papers on this, as have others. But there's also another interesting factor. Palladium is what's called paramagnetic. That means if you bring a magnetic field to it, you can interact with it. Take it away, and it's not magnetic anymore. But if you strain it, it will become ferromagnetic. It will become its own magnet. And you can imagine pumping enough hydrogen isotopes, hydrogen, deuterium, we didn't have tritium, you could expand the lattice enough to push it into that ferromagnetic, which gives rise to, if you will, another handle to drive these reactions. But that's a detail. We damaged the calorimeter, and that got me very suspicious.
Well, so what was the temperature spike? You think that so you see the temperature spike, the broken calorimeter, and you think that there's been fusion that's happened in there, or you're just
Well, I
like,
didn't
this
think
is
it was
weird?
fusion, but something strange had happened.
Hmm.
And the whole goal of this was to look for fast neutrons, which I think I didn't participate in the paper, but I think there was a paper that came out looking at this, but we didn't see very much in the way of neutrons coming out. Um, and that's always been the hallmark of fusion reactions. You should get the bulk of your energy coming out as fast neutrons, and so you look for those. Um, there is work that was done by one of my colleagues in India, who's actually one of the fathers, the 8 fathers of the hydrogen bomb in India. His name is Chino Srinivasan. He's passed away a few years ago. Um, he had done some of the very earliest measurements, literally the same day that the announcement was made in March 23rd of 1989. Being in India, he was already a day ahead. So they immediately set to doing a related experiment. And in the course of doing the experiment, they found that they didn't have that many neutrons, but they had a lot of tritium coming off, which got them wondering what was going on. He eventually published papers that showed that instead of in a classical hot fusion experiment, we have 50% of the time you're in what I'll call the neutron channel, and 50% of the time you're in the proton tritium channel. It favors by almost 10 million times the tritium channel. So you wouldn't see the neutrons. Now, there was no way at the time, and there really isn't a good way now, to say why that should be. I mean, even in hot fusion, the ratio is not 50-50. It's about 45-55, somewhere in there. And this mostly has to do with the masses of the reactant products and the differences between them, say between helium-3 and tritium. What else here?
Well, I'm just still trying to get this linear narrative. So the calorimeter breaking for you is some kind of light bulb moment where you think that
Yes,
there's an anomalous reaction that's happening.
yes,
And you said that there's an announcement on March 23rd of 1989. This is the announcement of the strange phenomenon in the calorimeter, or what's the announcement?
right. That was the announcement at the University of Utah prior to
Was that a
my
cold
even.
fusion announcement?
Yeah,
Yes,
I got you.
exactly.
I
Okay.
see. And so that's
That was the
Fleischmann
one.
Pons.
Yes, but now there's a lot more that seems to have gotten lost in the sauce. Um, prior to that meeting, Steve Jones at BYU, and I know all these people personally and have spent time in the BYU lab. Jones had proposed and written in, I think, Scientific American a couple years before, this idea that in the Earth's mantle, there might be nuclear reactions going on. And he was involved in trying to see if he could set things up to do this. In fact, I participated in an experiment with him, which had him making Portland cement with heavy water. And I said, "What do you think is going to happen?" Well, as it contracts, the deuterium in here might undergo fusion. I said, "Well, if that's the case, I want a contract so that I can lay this down in the northeast of the United States in sidewalks so that they will melt the ice automatically."
Did it work?
No, it didn't work.
Sunburns on everyone's feet, no big deal.
Yeah. No, it didn't work. But what happened was Stan, Pons, and Martin had put a proposal into the Department of Energy for doing this. And one of the reviewers of the proposal, this is prior to 89, was Steve Jones. So Jones spoke with them, and they went down to Jones's lab. And another friend of mine who's now passed away, Mike Mielich, was there. And it seemed pretty clear to them that Jones was going to try to scoop them. And they brought this to the attention of the president, University of Utah, Peterson, which is why they found themselves forced into this press conference they did not want to give.
Mm.
In addition, one of the things that's been suggested is that they had done published scientific data by press conference, which is not true. They had already submitted a paper and been accepted into one of the electrochemistry journals. They and Jones had more or less agreed that they would co-publish papers in different journals at the same time. I think Steve's was going to go into Nature, theirs was going to go into electrochemistry, because that's what they were, electrochemists. That kind of fell apart when the president of the University of Utah intervened, seeing dollar signs and patents in front of him, and everything went downhill from there.
Downhill how? It just became a hot topic that nobody wanted to touch, and people started saying that the results weren't true, because you said yourself that you saw the announcement and you were like, there's no way.
There's no way. Yeah, exactly. But I didn't know the backstory then. I didn't know the backstory until about 10 years ago, 20 years after the events.
Mm.
I used to visit with Martin in Tisbury, UK, whenever I was traveling back and forth. So he and I had chances to talk about this there and also at conferences here in the States and elsewhere. The real problem was, first, the chemists were very excited and the physicists were very irritated. The chemists thought this was cool, hot, that you could get nuclear reactions occurring in condensed matter. The physicists thought this was absolute baloney. And so there were some conferences beginning in March and into April and May that basically cast this great doubt on all of this. And this also interfered with the ability of Martin and Stan to do experiments. One of the experiments they had done, and I don't remember, I think it was after the March announcement, they had they'd set it up with about a 1 centimeter cube of palladium, and they had been electrolytically loading it. Stan Pons' son, teenage son, was in the lab with them, and he momentarily turned the power off, and Stan turned around and said, "What are you doing?" and turned the power back on. That night, the entire thing blew itself apart. Now, there have been a whole bunch of nonsense stories about this, but I talked to Martin about it, and I talked to a grad student who was in the department and will forever hate both Stan and Martin for what they did, i.e., creating a cast of doubt over the chemistry department at the University of Utah. He actually had trouble getting a job because of the taint.
Wow.
But what had happened was, apparently this thing had gone extraordinarily hot, vaporized almost everything in its little chamber, and made its way through the top of the table, which is usually kind of a fairly refractory asbestos-like material, went through that into the floor below the container, and it took out a piece in the concrete about the size of my thumb.
That's crazy.
Now, it's been reported it took out a piece the size of one's fist, a whole bunch. It's not, I don't think that's true at all. Stan and Martin were scared to death they were going to get into deep trouble. They immediately cleaned up the mess.
And
did that happen?
Never repeated it? Like,
what's the deal with turning these things on and off again? Like, what is? Did you follow that?
Well, I'm imagining that it's some kind of like shock compression that happens when the current goes back into it.
I think you are correct. I've talked to Martin about this. He completely disagrees, but be that as it may, I don't think he likes thinking about that episode, to be honest.
But that, hold on, but why not? I mean, that seems like such an insane.
So here's the way this works. You have a cathode, you have an anode wrapped around it. You are driving current in, you're probably approaching an amp per square centimeter, which means you're pushing all of these deuterium in. When the deuterium gas that's there, as you dissociate the water, the deuterons will separate on the surface. It's called spillover. And palladium is unique in that it will cause them to separate on the surface. It will cause them to become adsorbed, stuck to the surface, and then they'll become absorbed into the surface. So what that means is there's a gradient, all right, that you got it densest in the center and it kind of falls off on the outside. Now, when you turn the current off, it doesn't like being in there and it rushes out. If you turn the current back on and you do this, maybe there's a timing issue, you can imagine two waves passing by each other. That could be very unfortunate for the device, which I believe is what happened to them. It happened once at the US Navy Spay War with my colleague Pam Mosier-Boss. It happened to another colleague in France, and it made a mess.
But my instinct as a scientist would be that, okay, well, we should just make 1,000,000 of these and then just start flipping the current on and off until we can figure out what's happening. But Fleischmann doesn't want to talk about it? Like, that's so strange.
Well, he's dead now. He's
Well,
been dead for a decade, so he can't
he
talk about it.
doesn't talk much.
Yeah, well, you can ask him, but I'm not sure he'll get much of an answer.
But even at the time, like you're saying that he had a traumatized response to it where he just didn't want to repeat it. But you're saying that the same thing happened for you with the calorimeter as well.
Yeah.
So it's like,
Yep.
was this the seed for future like, are you
For
doing
like
this right
condensed
now?
matter fusion?
Yeah.
Like, is this the
Yeah, so one of the things that we've tried is using pulse sources, and other people have done this, trying to do it on a more gentle, because if the goal is to destroy the device, it's kind of one shot. You don't learn very much. And the other problem is that for the longest time, and it's still to the current day, if you don't see fast neutrons, then you don't have a reaction. Well, that may not be accurate. In the low energy nuclear reaction, aka cold fusion field, there seems to be a misconception that an alpha particle which finds electrons, fast alpha particle finding electrons, will become a helium nucleus. All they want is helium. They don't want anything else coming out. That might make a few people happy, but physicists say, where's the ash? What has happened? How do we know there was even a reaction? How do we know it wasn't just pure electrochemistry? The work that I'm on a patent with Pam Boss and Stan Spock, not Stan Pons, but Stan Spock and Frank Gordon, is called co-deposition. And the idea is to get around some of the problems in using bulk material. Because what happens is you start pushing things into it, it expands. Well, when things expand, they crack. So here you're working, heroically to get deuterium in, and all these little cracks, it's all leaking back out. So for one thing, it's very difficult to get the experiment to go using that. The co-deposition method we developed, which really grows out of Stan, and then Pam and I got involved with it, and Frank was kind of overseeing what we were doing, says, okay, let's build a lattice up one atom at a time. We'll put a palladium in, we'll put a deuteron in, we'll put another palladium and another deuteron. And by doing this, we start with an expanded lattice. It doesn't have to crack. The second thing is that instead of waiting potentially weeks to months for this chunk to load up, we can load in less than a week. And so now we've patented that. The patent came out in 2013. It's been used over 1,000 times worldwide.
And is this the same kind of atomic layer deposition that's used in making modern transistors?
One could say it's a similar way. It's an electrolytic way of doing the same thing. That's right.
Interesting. And so
Yeah.
are you getting for the pictures that are in your paper, it looks like there's
So we're moving into lattice confined fusion now, from what I can tell.
well, yes, but as far as I can tell, these experiments that Fleischmann was doing and the calorimeter was also lattice confined fusion. It just
Yes,
wasn't
Potentially.
like it wasn't termed as such, and nobody really knew what was happening. And so now,
Yeah. So I, just to give you a pause here, I did not coin the term lattice confinement fusion. I borrowed it from another colleague whose last name is Nee, N-E-E, up in Los Angeles, describing more conventional cold fusion things. And because cold fusion and low energy nuclear reactions have such a terrible nomenclature in the world, I was looking for a 3-letter acronym because you've got magnetic confinement fusion, and you've got inertial confinement fusion, and you've got magnetic inertial fusion, MIF. I thought we'll just add one more, LCF.
But
Yeah, it must be really hard to go to parties with other NASA scientists and say you're working on cold fusion. That must not go.
No, I don't do that. That's a bad idea.
but just between us,
Yeah.
you are
Blink
working.
twice.
Yeah, and your hundreds of thousands of listeners.
But I guess this is the question. Like, is there something that is categorically different between lattice confined fusion and the cold fusion projects of the
Okay,
of
yes,
the
I think
early
it's
days?
it's the deuterons, right?
Yeah.
No,
No?
it's both of them use deuterons. Okay,
Really?
it's
Okay.
yes and no. So here's the basis of it. We were charged in February of 2017 by Thomas Zurbuchen, who is the science mission director at NASA, assistant administrator. For whatever reason, NASA's top is not a secretary of NASA. He or she is the administrator, and all of the people below him are assistant administrators.
Oh, wow.
And he has some people in his office who are her office who are associate administrators. Thomas did not like what we were doing. We were requested to give a presentation on what we would like to do, and we gave him 3 choices. One choice, which we had done, was using the co-deposition. Another choice was using what I will call using a plasma to load things in. And unbeknownst to us, at the same time, Lawrence Berkeley Lab, under another colleague with Google money, was doing exactly that, but we wouldn't find out for about 5 years. And the third one was to follow up what we were doing using a linear accelerator. That we would use the linear accelerator. Let me back up here. A lot of people beginning in the mid-'80s, looking at some astrophysical anomalies, got interested in what I call and what they called laboratory astrophysics. We did, this really struck a chord with me because we did the same thing at the Laboratory for Laser Energetics using a laser to implode targets and look at the products and reach stellar temperatures and pressures. We had one scheme which for some years did not work, which we were able to produce microdiamonds by using the right material that we compressed. So at any rate, when I heard about the laboratory astrophysics, I thought this is really cool. And one of the books that I eventually got was by Klaus Rolfs.
Cauldrons in the Cosmos.
Yes, this is a really cool book. It's out of date now because a lot more has been added to it. And I don't think Klaus is going to add another edition, but it's a superb book. But what they were looking at is there were some anomalies, and I'm trying to locate the one. And I sent you folks some cutouts and some papers that was purportedly a difference between fluorine 19, which is stable, and I believe oxygen 18, which is also stable, but is only about, I think, 1% of oxygen terrestrially on Earth. One of the papers I found after you guys got me thinking about this again suggests that no, it's spectroscopic differences. We weren't as clever when this originally was done 20, 30 years ago. Now we're clever. But then I noticed, I highlighted in red, we make a few assumptions and we make a few things about convective cooling and heating, and we can come up with the right answer. And I'm thinking, I'm not sure that I've been thrown out with the baby and the bathwater. But the point is, and this was suggested by my business partner, Jay Kim, who's an economist. What happens if this Lehner reaction happens in stars? I said, I don't know. It kind of makes sense. So I began looking into it. And what it comes down to is in Proto-Stars, you have a gas cloud. If you have what we now call a population 1 star, where we've gone through the mill between population 2 and population 3 stars, lots of supernova, lots of metals. Metals to astronomers is anything from lithium on up. What's the chance that electron screening plays a role in the early formation of a protostar? So one of the things you guys have spurred me on to looking into is, okay, what recent data do we have, in particular from the James Webb Space Telescope, that might give me a clue on this, because it can see into the protostar gas cloud in the near infrared and in the mid infrared regions. So that's for another day, another paper, another fun. But
It tied us
this
back
whole
to the
thing of
differences between cold fusion and LCF, though, because that's how we started on this.
yeah, okay. So electron screening doesn't occur for particles that are over 10,000 electron volts. Each electron volt is about 11,000 degrees Celsius. So that means you're talking about something that's pretty hot. 10,000 times 11,000, you're talking hundreds of millions of degrees. The cold fusion work and the low energy nuclear reaction happens at room temperature. How could that possibly apply? Well, the laboratory astrophysics experiments, to the extent they could do them, find that this factor that describes the probability or the cross section of, let's say, deuterons getting together and getting really friendly goes to zero very quickly. Experimentally, these astrophysics experiments show that it in fact begins to come up as the energy goes down. There are no really good experiments below probably 2,000 electron volts, but you're already well into the region where electron screening begins to have a factor.
And the screening, just for people who haven't heard that term, this is a way in which energy is lost. This is
It's a way in which the electrons in a metal, in particular, or in a very, very dense plasma, shield the positive charges from each other by having a collection of all these electrons, all these negative charges around it.
and you want them not to be screened because they need to smash into each other and make.
No, you want them to be screened so they can smash into each other.
Oh, I got it backwards.
Yeah.
Hold on.
Yeah.
Let me think about that for a second.
So this is still a little bit hard for me to understand, and maybe this is because it's kind of the cutting edge of physics at this scale, where even if you have electrons, so from what I understand, electron screening is this property of the lattice where there's all of these atomic orbitals that are around that are able to make it so that the deuterons don't see that there's another positive charge nearby.
Hmm.
And so at some point, though, in order to actually squeeze them together, you do have to get the intervening material out of the way. And
Well,
so,
the intervening electrons.
yes. And so, but
But bear in mind, we're talking about quantum mechanical phenomena here.
mm,
Okay. The electrons themselves are basically, because of let's see what the best way to put this. They are not solitary. They are, in fact, moving at very high velocity. They already have a 1 to 2 keV energy. So it's not like your deuterons are surrounded by these fixed electrons. Everything is moving very rapidly, as are the deuterons themselves, but they weigh thousands of times more. So you now run into the business statistically, what can you do to enhance this effect happening? So that's kind of goes back to the original observation by Pons and Fleischmann. You have this momentary change in the number of electrons. And in a sense, this was part of the reason that I pushed that we do an accelerator with electrons. I mean, it would be much smarter, wouldn't it, to use an accelerator with deuterons and fire them into something. And in fact, that's been done. We've done it at NASA. But what I was trying to do was have the deuterons fixed and bring more electrons to the party.
mm,
And the two papers that we published in Physical Review C in 2020, one is a theory paper, one is an experimental paper. And to our great chagrin, they were within, I think, 10 or 15% theory predicting what we should see, which we saw. It's kind of sloppy because we had to throw out almost all of our neutrons so we wouldn't confuse them with the gamma rays produced by Bremsstrahlung or breaking radiation, where you take an electron beam, you hit, in this case, a piece of tantalum metal, and you produce gamma rays from it. Well, that's life, but it worked. What is also happening in here, which came out of the theory paper that Vlad Pines took the lead on, is there is actually 3 types of screening. The first type of screening is the conduction band of conductive metals. So you have electrons that are able to freely go back and forth, and this has to do with the Fermi surface, and this is a quantum mechanical effect. The second screening is the electrons, what we would call the core electrons and the valence electrons down of the metal that you're working with. And the third one, which I suspect is more important, is what I call the plasma screening. If you have a deuteron beam or you have a deuteron which has gotten itself excited, as it travels, it will drag electrons with it up until the point it reaches its Bragg peak, the point where it basically stops dead in whatever medium it is, whether it's gas or it's metal. Just before the Bragg peak, it's well into the electron screening region where there's enough electrons to say, hi guys, this is exciting, but you haven't stopped. You still have some kinetic energy. And I suspect that this is related to when these reactions occur. So those are 3 types of screening.
But so, how does the screening make it so that the deuterons can actually fuse? Right? Because you're still stuck. So, at the very beginning of this conversation, you're like, okay, so if you take 2 south poles of a magnet,
Yep.
yes, you can put them next to each other, and with great effort, you can make it so that they kind of hold in place. But the minute that you release the pressure, they're gonna blow apart. And so, what is actually? Do you have any insight onto what's actually happening that causes all of the sudden the analogy to the South Poles to no longer blow apart?
Well, the first thing I have using that analogy is that by, let's just say, switching the current or switching the frequency that you're pumping it with, that it's as if you took the north and the north poles and suddenly flip it around to the south pole. That's one supposition. I don't have a good answer to your question.
So then, if that was the case, wouldn't you just be able to pump AC current into this and then just be flipping everything over and over again?
Depends on the scale. Depends on the scale and the momentum of the particles that you've got in there. I have a colleague, Edmund Storms, who's retired after 45 years at Los Alamos, who's given this a great deal of thought. And one of the possibilities that he has is he calls it the nuclear active environment. It is a channel which is, in his mind, small enough to support the formation of molecular deuterium, but large enough that it can interact along this linear path. Now, I don't know if that's correct or not. We've done some density functional theory codes, and we've found that, in fact, if that is real, it is very sensitive to, if you will, the sides of the material, the spacing between them. It's sensitive to a fraction of an angstrom. So it kind of lends credence that there may be something that we could potentially in the future make using, let's just say, semiconductor processes to make little trenches or something like that. No idea, haven't tried it. But your question does not have an answer as yet. All we know is we see the products coming out.
That's so fascinating.
And we also have the problem with co-deposition that we see the products that most of that field does not want to see, because we actually have published a paper where we've seen roughly an equal number of tritons to helium-3 coming out by measuring the protons and the neutrons coming out of the reaction. The consequence is they've declared what we're doing hot fusion. I don't care what you call it. We know that it works. It's been used in multiple US labs in the Navy and at NASA and other places.
It's called hot fusion because there's a high energy beam involved. Is that?
There's no beam. We're running at 5 volts.
But there's a laser of some sort, right?
Not for the co-deposition.
I see. This is just production.
We don't use a laser.
Just producing the fuel. Yeah.
Yeah, it's just, we co-deposit, so it's a very high density.
And so why do they call it hot fusion?
No, they don't call what we're doing hot fusion.
Oh,
Well, let me back up. Because we see the products of hot fusion using co-deposition, um, the low energy nuclear reaction community says, well, we're just doing hot fusion. And that's fine. If we're doing hot fusion at 5 volts, that's very efficient.
interesting. Okay, so
Because the
there's
fuel is constructed
because
this way.
yeah. So do you feel like you're kind of at a place where, in order to understand what's going on, we're gonna need some deeper level understanding of nuclear physics?
Yes.
Are,
But, I'm not sure that we do. I don't think if the electron screening hypothesis is both um, one of the governing things, but not sufficient to drive these reactions, we don't need any new physics. Electron screening has been known since Saltpeter's paper in 1954, and actually it's got some uh, precedents going back to the late 40s where people looked at this again from the perspective of astrophysics. And in fact, Saltpeter was on sabbatical from Cornell University, published this paper in 1954. I think I sent it on to you. Uh, and he was looking at what he called weak and strong screening and its effect on astrophysics. We've just borrowed that, and then, you go 30, 35 years later, you got a group of people playing with this in the laboratory astrophysics. One of the things that came out of those experiments is some of the results that seem to indicate that this thing called the gamma factor, which is this probability that you can get them to fuse, may in fact be itself a function of the surface of the material. So, they've done experiments at very high vacuums, I think 10 to the minus 12 torr. And at 760 torr is room pressure, STP. So there's very few molecules in there. But the surface has got typically oxygen and sometimes it's got carbon on it and stuff. One of the papers published a decade ago said maybe these screening results are as much a function of the contamination of the surface. So you're firing a deuteron beam in, and it's interacting with the surface. Now, from an electrochemistry point of view, that makes perfect sense. What's happening is you're going through that surface, but that surface allows you to retain the deuterium inside. It prevents recombination. These are really hard things to do. And I have colleagues at Mitsubishi, which did a beautiful experiment. They took a diffusion experiment. They took layers of palladium and palladium oxide, and on the top they would put cerium. No, is that right? Cerium? Cesium, strontium, and barium. And on that side, there was vacuum. And on the other side, they would put D2 gas under pressure. They would then force the gas through these layers till it hit the top layer. Then they're using an electron beam to measure what's happening on the surface. So you're doing essentially you're doing EDAX. So electron, you're not even diffraction, you're doing elemental analysis. It's a very poor technique in that it's only sensitive to about 1 part in 10,000. So you start off running the experiment, and you see all these cesium atoms by the X-rays coming off that is being picked up by the electron beam exciting them. As the experiment runs, it starts turning into disoprisium. It's gone up in the periodic table. The same thing has happened with the strontium and the barium. No idea why this is working.
So they're
Except that
actually turning into different elements in the presence
yeah,
of this unequalized deuterium gradient?
that would be what was published. And the work was then also replicated in Toyota Central Labs in Japan and at Osaka University. The problem was the Naval Research Lab got involved. They tried to replicate this and couldn't.
Hmm.
They sent one of their people there, and he went swiping around inside Uemura's lab and found out that, well, there's dysprenium in here and it's a contaminant, and so you're not measuring anything that wasn't there to begin with. Which eventually those findings by NRL, which did not take on the strontium, did not take on the barium results, resulted in that program being shut down. Now you can imagine why they were doing it. They were looking for an inexpensive way to turn nuclear waste into something that was either harmless or, better yet, worth money. Now, there's one more piece to this. Before he left, I met with Imamura, I think in Korea, and I said, the work that NRL did is they analyzed the pieces that you had, and they used what's called inductively coupled plasma mass spectroscopy to see if there were elemental anomalies and things like that, as had Osaka and the Toyota people. Apparently, they claimed they hadn't seen any because they didn't see anything other than what they expected to see, which was the cesium. I asked Iwamura, have you ever done the experiment and not turned on the electron beam and then done the ICP mass spec? Because what you're doing, I suspect still, is you're bringing a lot more electrons to the party. You're getting a lot more screening going on. And those poor deuterons just minding their own business, trying to get out of there because there's vacuum on the other side, find that they're suddenly being caught by the cesium or the strontium or the barium. That experiment has not been done.
That's wild, because that seems like a really first line control. Interesting.
You'd
Okay.
think. A lot of these experiments, companies don't want to do it. I was amazed that Toyota Central Labs was willing to do this. And this is years after Mr. Toyota had set up the Pons and Fleischmann lab in Valbonne, France. They had actually run there for a number of years.
I'd like to imagine that the people that are engineers at the highest level are also deeply fascinated by these fundamental science questions. Because I know that IBM had an astrophysics lab for a while. Like they were putting out astrophysics papers, and
So IBM is a funny case here. It in fact, what happened there gave rise to a lot of the problems that this field has had from its get-go. When the 1989 announcement came out, Jim Ziegler, who was at IBM, as was one of his colleagues, and he proceeded to do these experiments. They're very clever. He had a piece of palladium. He put a layer of gold on the back so that it was coming in from the anode and the germ would go in there. And then he put what's called a silicon surface barrier detector, detects charged particles, right up against it. And he must have done 20 or 30 experiments. I kind of got to know Jim over the phone. He and I were supposed to have a lunch date at his favorite crab shack near Annapolis. And he unfortunately then died. And so I didn't see him. So bear in mind, you guys talking to me.
No, many more years.
But here's the funny part. We all assume that Jim, having written this piece of code called SRIM and TRIM for looking at the interactions of ions in matter, in condensed matter, whether it's gas or solid, doesn't matter. It's used around the world. Anybody doing proton irradiation of people or of anything, they use his code. I assumed that he had used his code himself. He hadn't. It took my colleague Pam Mosier Boss to say, well, okay, I know how thick his palladium sample is, and I know how thick the gold is, and I know how thick the chrome was that allowed the gold to stick to the palladium. And when she ran his code, she found out that if in fact he was making fast protons or fast alphas, they would never make it to the silicon surface barrier detector. They would get stopped inside. So that was kind of unfortunate. But we didn't realize that for 20 years. And we published a paper on it.
Yeah, I mean, I think that this must be the case for a ton of experiments in this space, just because it's so unbelievably complex. The process of detection is not straightforward.
No.
Anytime that you build a new system, you have to understand all of these different parameters, and you have to be an expert in everything from, circuit design to programming to materials chemistry and electrochemistry, and it's just there must be a relatively narrow window of people that have the expertise that actually allows them to build and test these systems.
I think that's true. And there's a lot of people who have some of the background and have not had a lot of success and then say, well, this doesn't work.
Yeah.
The person that really made this whole area verboten was Dick Garwin.
Hmm.
And Richard was one of the Jasons. I don't know if you know who the Jason are.
Mm-mm.
So the Jason was formed shortly after World War II as a independent group, independent of the government, who could weigh in on Pentagon interested, other government interested things. They would be able to bring scientific and engineering talents to look at a problem, sometimes classified. And Richard and one of his colleagues, who's a professor emeritus at Princeton, well, up until Dick passed away a few months ago, were the last, I think, surviving members of the second cohort in there. Now, it turns out Pam Boss and I gave Dick a review of our work with CODEP. And it was a very interesting time because she put the first slide up, was reading the title of the slide, and Dick says very gruffly, "I can read." Okay. So we just kept putting the slides up, and we get to the last two slides. I always put in some theoretical possibilities. And I mentioned electron screening, and I thought Dick was choking. I thought he was having some kind of fit. Turns out he was laughing. And I said, "Why?" He says, "Oh, so that's what it's called now." I then found out later, after he met with some other colleagues and then did some digging into his background, during the Ivy Mike thermonuclear test, he worked for Carson Marks, a Canadian physicist, and did some calculations, which turned out involved electron screening. What happens in the fireball if you're trying to do a fusion reaction? Does it change anything? And concluded it doesn't. Now, that was all classified then. And that's why he said, "Oh, that's why they call it electron screening." That was, and he told me that was classified when I did the work. I did the calculations. What he didn't know was the density of the fireball was orders of magnitude lower than what you get in condensed matter, and very short-lived.
That checks out.
But on the basis of that experience in 1952 and with Jim in 1989 at IBM, he kind of made it his life's work to make sure that this field went away.
Man, that's
He
wild.
interfered with our group at NASA twice.
Like tried to get your funding cut?
Yes, exactly.
Wow.
He even offered a good friend of mine's who was an administrator, assistant administrator, offered him, "When you leave government service, I can see that you become a Jason if you want. Just make them go away."
Hey guys, quick interruption. Remember, this podcast is entirely paid for by you, the listener. It means we don't work for anybody else but you, but we need your help. So you're going to have to come over and see if you can spare 75 cents a week to keep this thing going. And you can find out more over at patreon.com/DemystifySci. So I wanted to understand why this guy, well, can you remind me the dude's name that you...
Dick Garland.
Garland, yeah.
Dick Garwin.
What?
Garwin.
Yeah, like
Richard Garwin, and he just
Garwin.
passed away
I
recently.
see. So I
As they
understand
say-
Garwin didn't expect this kind of thing in these nuclear fireballs, but why was he so opposed to it occurring on the instruments themselves when you guys started presenting this?
Largely because the person who did the experiment, well, Dick was, let's put it this way. When Jim wrote the paper, if you look in the acknowledgement, he mentions Dick Garwin. Dick was at IBM at the same time that Jim was at IBM writing these codes, because what was happening was IBM was making use of beams of phosphorus and boron to basically load up to make semiconductor sheets on the whole wafer. And they needed to know, what's the damage threshold? How deep will it go? So Jim wrote a series of codes that are used to this day. And you can tell that they originally were designed for a DOS machine. I mean, that's how far back they go.
Still working.
Still working. I still use it. Although my current Mac, I've not tried putting parallel. I don't know if you guys use Macs or not.
Mhm.
So Parallels is much better than Boot Camp or whatever that is. That's the alternative. So you can run Microsoft products on a Mac. And the problem I've got is my Mac is an M1. So it's only been the last year that Parallels has been working, and I've not gone to the trouble to put Windows whatever on there. But my major fear is that the Rosetta 2, which converts Intel code to M code, won't work. So I have an ancient 13-year-old, pushing 14-year-old Mac with an Intel processor, and I run the code on that.
It's good to keep some old computers around. I've run into this problem recently too, like trying to update firmwares and things where it's like there's absolutely no solution except for an earlier generation computer.
Yeah, exactly
So
right.
we have an old Mac that's just barely, like, it can't even hardly stay on. But if you need it in an emergency, it will help with
there.
your hardware.
I think that thing is from 2013.
I think so.
And it's just,
Oh!
it chugs along barely.
That's my machine.
That was
I
a
love
good
it.
model. That was a really good model.
Well, no, it's more than that. Whenever I bring it in to, for instance, I had the disk drive taken out and instead had a solid state drive put in with twice the capacity, and that was wonderful. Then I also installed twice the memory, so it now has 16 gigabytes, even though it's only supposed to have 8. But they had quite wisely put the address lines on.
Yeah,
So it works.
they've made the Macs progressively harder and harder to work on. Like, I've replaced components on old ones, and you know the iFixit guides. You like pull it open and you're just kind of dealing with it. But I replaced the battery on Shiloh's old iPhone, and I was struck by just how impenetrable the entire thing was.
Oh yeah. Yeah, and it's not just the fact that it's gone to, even ever smaller surface mount components. It's the way it's put together so you can't work on it.
Yeah, they're literally.
And even when we did work on it, they forced me into upgrading in some other software-based way eventually.
Well, yeah, because they just stop working suddenly. Like there's software problems that arise, and you can attribute that to just like creep of replacement of engineers and not rewriting code and all of the like different hardware stack that they're trying to run it on. But it also is deeply convenient in terms of making sure that you buy a new machine.
All right, we're getting off topic though, because we don't have a ton of time left. And I really have there's a lot of pieces of the story we gotta.
If you're in San Diego, we should do this over coffee because we're in San Diego at least once a year.
Oh, you are?
Oh, yeah.
Well, when are you next time coming down?
Probably around Christmas.
Okay. Chances are I'll be on the East Coast.
Well, we'll figure it out.
Yeah, well, we're all over California, so.
Give me a heads up. That would be cool.
For sure.
I wouldn't recommend surfing, though. The water's cold here. Yeah. Not like yours, but cold.
This is true.
Cold plus sharks. Bad combination. Okay, so this gentleman, is the gentleman in question wrote the code that's used to this point, or his friend?
So there's a guy at IBM.
His competitor wrote this code.
Jim Ziegler wrote the code that is called SRIM TRIM, and you can get it on the web for free.
Okay, and remind me of the original gentleman's name.
Dick Garwin.
Richard Garwin.
Garwin.
We knew him as Dick.
Dick and Jim are the two characters here.
We dealt with him.
So Ziegler is at IBM. And
at the time,
and he's just kind of interested, and so he puts together a device to see if this is actually happening. And
precisely,
the problem is that Larry and his colleague Pam went back through, analyzed the device and the code, and was like, the device is built in such a way that even if these reactions were occurring, the structure of the device would prevent them from getting to the silicon layer that's the backboard of it, that is the detection layer.
Yes, and so she's that's exactly right.
It invalidates only his experimental setup, not the process itself.
Cool.
Precisely.
But Garwin had run these simulations during, you said it was like the IV something?
No, he didn't do any simulations. What he did is, this was in 1952, so I don't even think, well, he probably had access to ENIAC and maybe even MANIAC computers, but I'm guessing he did this by hand. So Carson Marks had charged him with doing some of the calculations that Marx was responsible for to describe what might happen if they used an atomic bomb to set off 20,000 liters of liquid deuterium. That worked. It was like a 5 megaton explosion.
Wait, did they actually run this? Or-
Yes, they did it out in the Marshall Islands. That was the first human-produced fusion reaction. I would argue it was the second because people didn't recognize the first one.
Which is the Fleischmann stuff.
Nope.
No.
That was 89.
Oh,
No.
yeah.
So if you remember, Ed Teller pissed off everybody during the Manhattan Project at Los Alamos. He eventually was more or less kicked out by the then director because he was just making life hell. This is after the Manhattan Project. And so he, through his various friends, got the Lawrence Livermore setup. That created Lawrence Livermore. So the first thing they did is, they're doing testing out in the Nevada test site with devices built by Los Alamos. So he thought he would build his own devices. So the first one was highly enriched uranium with hydrogen on a 300-foot tower. And when they detonated it, there was 100 feet of tower left. Los Alamos thought this was funny as hell. So the next shot he did, he replaced the hydrogen with deuterium and had a shorter structure, like 100 feet tall, and set it off, and it removed the structure. But Los Alamos thought this was pretty funny too. My supposition is that what happened in the second case is he initiated a thermonuclear burn. And they weren't set up to look for 14 MeV DT fusion neutrons. Had no idea. Now, the reason that it didn't do more damage was as soon as that thing went off, it just pulled itself apart. And so what we refer to as the alpha factor never made it to the point where most of the material was burned, so to speak. So it was a fizzle. There's no data that I'm aware of to confirm or deny this particular supposition.
Okay, so tie this to the Garwin character.
So Garwin worked on the later one in 52, which is I think this one was done in 50 or 51. Garwin was part of Jim Ziegler's project in that he consulted regularly on it, and so he saw that Jim, who's the expert on ions and condensed matter, saw nothing, therefore there's nothing there. End of story.
Got it.
And Garwin carried that all the way through until he passed away.
I see. So he believed in the fidelity of the experiment. He thought the design was sufficient to answer this question. All right.
Now there's another person that comes into play here, John Heisinger. John was lured from Argonne National Lab in the mid-60s to the University of Rochester, where they promised they would build him an accelerator, and it was a tandem Van de Graaff. So he could continue doing what he called what was then called nuclear chemistry, where you would fire protons, deuterons, alpha particles at typically uranium, or if you got your hands on some neptunium, or if you really got your hands on some plutonium, all in support of the Atomic Energy Commission's bomb side of things. So he's doing unclassified work at the University of Rochester using nuclear structures and coming up with cross sections. All right, gainfully employed. The rest of his time, he's irritating undergraduates like me in our courses.
What that term cross section? You've used that before. Can you tell people what that means?
So the cross section is measured in something called barns, and a barn is an incredibly small area. It's 10 to the minus 24 centimeters squared. The reason it came up is they didn't know at the beginning of the Manhattan Project what the probability that a thermal neutron might fission something like uranium-235. And they were trying to decide, was it 235 or 238? That actually was known back in Europe prior to this. But when they finally started making the measurements carefully, they found out, and somebody declared, boy, the cross section's as big as a barn door. Hence, 10 to the minus 24 is a barn.
So it's like a density measure?
It's an area measurement.
Okay.
So it's like a
And
flux?
well, no, think of it this way. You have a neutron and it sees a nucleus. The neutron and the nucleus are both wave functions. At low energy, the neutron presents a very wide wave function to a nucleus. And that's where this whole thing comes in. What's the probability that this neutron coming in will interact with the nucleus? And it's got several different things that can happen. You can scatter, you come in and you bounce off. It's an N prime reaction. You can get it captured. That'll give you typically an N gamma reaction, depending on what you're doing. It may do some more things. You can get spallation if it's got a little more energy, or it gets things excited enough that you'll kick off a neutron, becomes an N2N reaction, or you can get a proton or an alpha coming out. There's a bunch of things you can do. If you've got the right material, it may in fact fission. So U-235 will go to U-236. And depending on how unhappy it is, it may in fact split into two unequal parts, sometimes three, with the production of typically 2.5, roughly, neutrons per fission. That's where you get your chain reaction from.
Okay, so these low energy neutrons, they have a large cross section?
Yeah.
I see.
530 barns. That's a lot of barn doors.
Okay, let's pivot this back to the stars, because there's a drama unfolding over the 20th century with respect to how the stars power themselves as well, right?
Oh, yes.
and it's kind of nebulous to me, because I know that Eddington gets a lot of credit for this, but I went back and it seems like in his lecture he just kind of hand waves at the possibility that like something interesting is happening in stars, but he doesn't really propose fusion per se.
No, he doesn't.
Do you have a sense of the history of how this became the backbone of stellar astrophysics?
Yeah, I mean, a long time ago, I knew more detail of that because of the last 10 years, I've mostly looked at Fred Hoyle's work, where he conjectured that there was a resonance, I think, of 7.6 MeV in carbon-12, which had not been seen. And it turns out he was off by about a half an MeV, just working things out. But that's what gave rise to the tri-alpha. That if you had a sufficiently dense hot star, you could begin carbon burning. And this was, for the longest time, this was a problem, because how do you get to carbon, let alone oxygen, neon, everybody else? So it was his calculation that kind of came up with where this might fit. I don't think he got enough credit for that. He got credit for the steady state universe, which is not real either. That kind of trounced him. He thought hydrogen was being made at the rate of, I think, 1 hydrogen atom per every cubic meter of space per year or something, that would account for the expanding universe. And that didn't go over well.
But like long before Hoyle, there was people were starting to play with this idea. Was it Beth was the original fusion scientist? Beth?
Yeah. Well, yeah. Hans Bethe had a real interesting thing. I caught him in a lecture once at University of Rochester, probably 2 years before he passed away. He's a really interesting person. My acquaintance with his work is mostly not that. It's in stripping reactions. I don't know if you're familiar with those. Mm-mm. So this is where a deuteron comes close to another nucleus, and because the deuteron is so loosely bound, about 10% of the time, it is actually outside the strong force. You'd think, well, then why don't they all fall apart? Well, it's a wave function. It's moving around. But the point is that if there's another sufficiently strong, both a combination of electromagnetic and strong force nearby, you can strip off the neutron or the proton. And this was the Oppenheimer-Phillips reaction that was published in, I think, 35, and then Hans came by in 38 and refined it further. And so some of the work that we did with the accelerator was to see if we could actually pinpoint his conjecture. Because his idea was, if you have the number of protons of the atom at Z is less than 25, then you have equal probability of capturing the neutron or the proton. If it's over 25, it will preferentially pull in the neutron. Because what will happen is the proton will be shielded and move away. We shot titanium, which has got a Z of 22, and erbium, which is a Z of 68. That was great. The problem was the erbium half-lives, first of all, it would tend to go towards stable erbium. It's got 5 stable isotopes. And the ones that aren't stable, or might go to holmium up lower, or go to thulium, I think it's thulium, terbium, up one higher, we couldn't see them because the half-lives didn't match what we were doing. So we hadn't done enough digging to figure out what we should be using, but that wasn't what we were supposed to be doing anyway. What we were supposed to be doing was to see if we could induce fusion in condensed matter, which we did. These were side projects.
So nobody, and I believe none of these astrophysical paradigms that we've built up over the last 100 years have involved stars containing condensed matter in any real appreciable amounts.
I don't think that's true. You look at the density of a white dwarf star, that's definitely condensed. The neutron star is really condensed.
So we're only talking about these ultra-dense objects when you're thinking about the possibility of lattice confinement in these stars?
No, what I'm thinking is that this may be a means to assist the initiation of high metallicity stars. So if you've got a star, you start with population 3 stars born shortly after the Big Bang. They're basically hydrogen, helium, end of story. They undergo supernova. You get some building. You probably get, I'm guessing you get as high as silicon.
So the fusion reactions that make these next levels of elements happen in the shock waves of supernova.
Exactly. And you also have the problem that you get neutrino disruption, because you got an incredible neutrino flux coming out during a supernova. So a lot of what you've just made disintegrates.
But some of it persists and can be incorporated into the next generation and so on.
Otherwise, we wouldn't be here.
So you have these large elements. Are they forming lattices inside of the cores of these?
No. You don't need that. But what you've got is, as the proto-disk begins to collapse, the density is going up. At some point, it becomes dense enough and you initiate burning. And depending upon the amount of mass you've got, you will do potentially deuterium burning, lithium burning, and eventually you get in one of the PP cycles in that protodisk. The only question is there something that hastens the earlier deuterium and lithium burning that would be distinguishable from what current models say should be going on? And the fluorine is what caught me initially. The idea was that these large gas giants with huge clouds of relatively low temperature, 5,000 degrees Kelvin. Exactly. But you've got a constant outflow of material from that star. And what had caught my eye early on, which may have been an erroneous thing, is that the fluorine 19, and I believe it would have been oxygen 18 ratio, was off.
Okay.
And so then the question becomes, why would it be off? I think this was one of, and I may have picked this up somewhere in the last 15 years, talking to one of the folks, might have been Rolf, it might have been Zursky, relating to what got them into doing laboratory astrophysics. It's to account for something that we don't understand. And electron screening became kind of the major issue that was probably enhancing these. Well, if that's enhancing these, then that implies that you get nuclear reactions occurring at lower temperatures than you would expect, but probably higher densities than you'd expect. So the question then becomes, within the protostar disk, where might the conditions be right to initiate essentially a thermonuclear burn of whatever you've got in there, enhanced either in time or material that gives rise to this? And would that give you a signature that we now would be able to see with James Webb, because we can see into that proto disk?
But doesn't
That's
that still implies some forms of condensed matter in the ingredient pile for these proto-stars, doesn't it?
Yeah, well, that sure, but it doesn't have to be a lattice.
Okay, explain that.
Well,
You're just talking about
look at a
really
tokamak.
cold spots or something? Or?
No, look at a tokamak. That's not solid. That's a gas. You get fusion going on in there. You just have to work heroically to make it happen. That's all.
Would
So
you
the thought is, go ahead.
would you expect to see that kind of let me see if I can put this succinctly. So my mental image of a tokamak is that the confinement is obvious to the naked eye. Is that true
Okay.
or not?
Yeah, you can look in there with the camera and you can see it, and there are pictures of it.
And so
Yes.
if a similar thing was happening inside of a protoplanetary disk, like as far as I understand the model for nebular collapse, it's gravitation alone. Like there's
Yes.
not this kind of massive squeezing that you would
Well,
get inside of a Tokamak.
gravitationally over time does exactly that. And the second thing is electric fields and magnetic fields play a role. I've been pushing for what, 8 years now to get the Rubin telescope down in Chile that just is seeing first light. They have, as I remember, there are 6 bins for filters. One of the bins is open. I've been pushing them to put in polarizing filters in there so that we could measure magnetic fields in that area. And I have another reason for doing this, but that hasn't happened yet. What I was told some years ago is if I put up the money, they'll do it.
That seems like a non-offer in some ways.
So are we robbing a bank or what? Yeah.
But so, I guess the piece that is still a little bit mysterious to me is, so do you imagine that there's just like a much larger contribution of magnetic fields to stellar formation than we currently realize?
It is possible. There's a number of theories which I think are bogus. That one is called the electric universe, and it harpens on all of these electric fields that are causing compression things. And I don't think any of this is realistic, to be honest. But the a
The
collapse of
magnetic field, the magnetic universe, on the other hand.
maybe. To be honest, I haven't paid attention to these two theories in over 10 years. We got hit up by somebody associated with the Army and also up in Canada that really wanted us to run one of their devices at NASA Glenn Research Center. And I said, well, I don't know. How much are you willing to give us? Oh, no, you'd pay for it. I said, thank you very much. Bye.
Wow.
Okay, so, but, all right. There's a link between lattice confined fusion and the stellar processes that we're talking about now.
And that's the point. And don't stick yourself on the need for a lattice.
But why wouldn't there be condensed matter at the heart of a gravitating system? Like,
There is.
we know there's a bunch of junk out there, right, in
Yeah.
space. And why wouldn't we expect it to play a role in confining fuel sources naturally?
Because people have not paid attention to it. I'll give you a case example. Actually, two. One is the Earth, one is Jupiter. The question is Jupiter warmer than we think it should be because of some residual something in there? Are there, in fact, as with the Earth, are there uranium and thorium, which was in the cloud as well? Don't know. But it's warmer than it should be. The Earth is a more interesting one. Tritium has a half-life of 12.3 years. there have been a number of papers written. First one, I believe, probably from the late 60s, looking at one of the seamounts at the end of the Hawaiian chain, and they found tritium.
Hmm.
Well, that was attributed to, oh, it must be left over from thermonuclear testing. All right, end of story. We stopped doing open air nuclear testing, and tritium has continued to be found in odd places. The one that's my favorite one are lakes in China, where they find tritium down towards the bottom. And I ran into one of the authors of one of these at a conference in Sicily years ago. And somewhere I have one of his papers in English on this. And the question is, where does the tritium anomaly come from? This goes all the way back to Steve Jones, who was trying to make Portland cement using heavy water. And his conjecture was at the time, and probably still is, that you get deuterium locked within the mantle during plate tectonics, and you have you have a variety of more or less high Z metallic, like olivine, which is metallic but it's oxides. And so his conjecture was that there are conditions where this happens. That's where the tritium comes from. Don't know if that's true.
And might something like that be happening in these stellar nurseries as well?
That's what I'm thinking.
Yeah, interesting.
Yeah, this is not an original idea. I've just been pushing it further because of the work that we've done. And I would just relax the need for the lattice. But you want to have sufficiently high density and sufficiently high electrons and sufficient mobility of, if you'll call it, nuclear active material, which could be protons, deuterons, won't be any tritons, but lithium. And one of the things that
I still
Go
don't
ahead.
understand why you're saying like relax the need for the lattice, even though it seems like there could be a lattice. There could be condensed matter in these.
What would make the lattice? Why would the lattice exist?
Just from, I don't know, any form of condensed matter. Like condensation reactions are super low energy and downhill. I would imagine there'd be all sorts of just condensed junk in space, like droplet level
So
stuff.
you've just become the co-author on the paper.
Heck yeah.
Excellent.
Yeah.
So, dumb question. Isn't Jupiter supposed to be, at least in some substantive part, liquid metallic hydrogen?
Yes.
Is liquid metallic hydrogen capable of forming a lattice?
Don't know.
I see.
I mean, in liquids in general, it's like the word lattice becomes problematic for liquids because it's certainly more of a transient lattice, from what I understand.
Yeah, but here's the thing: if it behaves, if it is a quasi lattice that in time, that may be sufficient, and that has to do with the various juxtapositions. One of the counters to this working in liquid is work done by a colleague of mine, Kitamura, where he actually fired deuteron beams into liquid lithium and solid lithium. And he saw lattice confinement fusion reactions with the solid, but not with the liquid, which tells me that in the liquid
as
state,
evidenced by neutrons. Yeah, that's the
Yes.
problem. Maybe.
Oh, the neutrons are happy to get out. They're fast neutrons.
That the water doesn't eat them.
It's not water, lithium.
Oh, sorry. I'm sorry. The liquid. Okay. Sorry. The liquid doesn't swallow them. I see.
But one of the things that I'm interested in is if you look at the cycle of brown dwarfs that are burning deuterium, may have burned lithium for a bit, is the ratio of lithium-6 to lithium-7 off in these stars. And there are a lot more brown dwarfs than there are all the other stars. So again, this is where James Webb comes in. It can see them. It can spectrally resolve what's there. And are there, in fact, issues with lithium-6, lithium-7?
Interesting.
Are you preferentially burning one over the other? And if so, why?
If it was,
And again, it comes back to cross-section.
if it was preferentially burning one over the other, what would that tell you?
Something that was not expected was happening. It may not be this. It may be something else.
But it may be this.
Yeah. So in terms of things that are unexpected, fusion supposed to produce gamma rays?
It can. Different one, like the HD reaction produces a gamma ray, but generally it does not.
Is that
But there are secondary and tertiary, and there's a low probability that you can get a gamma rays out. In fact, one of the reactions that is favored by the cold fusion Leonard community is that you can go directly from DD to helium-4. Now, there's a small problem with conservation laws in doing that. There was one measurement made by a Korean scientist, and I don't even remember where the paper was. It's again over a decade ago, where he claimed that he had observed this very rare 10 to the minus 6 reaction, but it produces a 24 MeV gamma ray. I don't know if either of you have ever done gamma ray spectroscopy.
mm-mm.
It's hard to do as the energy goes up. Most gamma ray spectroscopy with a reasonable sized crystal, about the size of my coffee cup, tops out at about 3 MeV. If you get a really large sodium iodide detector, you can get out to 10 to 12 MeV. I've never tried going after a 24 MeV gamma ray.
Why'd you ask about gamma rays?
Just something that I was thinking about when it comes to fusion reactions and whether or not the radiation profile off of stars can give you any kind of clue to what's actually happening
Oh, I
inside
like
of them.
that. I'm gonna make a note of that one. That's good.
Have you heard of Shabilsky's star?
Yes, as a matter of fact, aren't those Wolf Sievert type stars?
That sounds right. But it's just a single star, from what I understand. But
Right, they've only found one.
they found one, and it seems to have these very heavy, short-lived isotopes that don't totally make sense. They kind of hint at aliens or some nuclear process in the outer layers of the stars that we're not aware of yet.
That's really cool. And I presume that is it in our galaxy?
I think so. Gosh, I'm embarrassed about this now. Yeah, I've gone so far as to read the Wikipedia page, so I'm no expert on the matter. But I do know that it was that it's. I mean, it's also spectroscopic evidence, right? So
Right.
if there's any kind of condensed matter chemistry in the corona or anything strange, like we might be misunderstanding what's happening. But
Oh, like the fluorine 19 problem.
it's,
That wasn't.
it's an interesting case, but it's funny because at least on the Wikipedia page, they're like, well, I guess it's, most people come down on the side of like, well, maybe it's just aliens like dumping their trash in the sun or something like that. And it's like, maybe, but it's got to be something.
I don't think so.
Yeah.
Trash like that would be too valuable to drop into a star.
Maybe they know something that we don't.
Well, you have to take that up with the UAP people.
Indeed.
Okay, so I actually think we should talk to some of these cold fusion people. And what would you like? What kind of questions, if you were sitting across the table from one of these? Because there are a few characters out there.
Do you know Bob Grenier?
I do.
So we have a talk scheduled with Bob Grenier, I think, next week.
Oh, good.
Yeah, what would you say to Bob if you? What kind of questions would you have for him?
Ask him about the banking difficulties he had when he had to leave the UK.
No, I'm intriguing. Scandalous.
Yeah, he was associated with Charter Bank, which it was not his doing, but they got into deep trouble.
It's funny because there's this other guy, Malcolm Bendall, that's also like in this space.
I don't know if I know that name.
He's like working on.
He also had investment.
He also had investment troubles. This is the problem with a lot of the alternative space, is that you start to get real odd characters that have perhaps.
You start coming up with creative fundraising schemes when you don't have access to a state budget, I suppose. That's the charitable way of looking at it. But no, what kind of scientific questions would you have about that work?
Well, so he was instrumental, and actually I was there in Korea and videotaped him with 3 other colleagues setting up the Martin Fleischmann Memorial Project. You might ask him if the project bore fruit in his mind, and if not, why not?
Mm-hmm.
Well, I think that from what I've seen of his work, he's absolutely convinced that they're getting these heavy elements on the insides of their devices, and they're doing spectroscopy and demonstrating that they're getting, you know, heavy element production from these deuterium reactions.
So as it turns out, we've done SEM EDX and ICP mass spec of our CODEP experiments, and we've published probably at least 5, maybe as many as 10 papers where we've observed the same thing. One of the weirdest ones, which I believe we published, um, when you take, say, a disk, a foil of palladium, and you electrolytically load it, and then we tried to seal the surface with mercuric sulfate so that it wouldn't deload. And we found out that as soon as we turned off the current, all these little bubbles appeared on the surface, meaning it was deloading. What that also does, and this goes all the way back to what happened to Martin and happened to some, Jean-Paul Bavarian's experiment in Marseille and our work at SPAWAR. When you look at the bubbles on this little foil, let's say an inch on a side under a microscope, you can see all these things that Pam Mosier-Boss and I call barnacles. When you take an SEM EDX and you go inside what's inside the barnacle, you're astonished to find that there is, let's see, it's aluminum, it's carborundum, little needles of carborundum that are like probably about 2 to 3 microns long. There was no aluminum in there to begin with. And in fact, from an electrolytic point of view, when you run a CODEP experiment, this was CODEP onto a foil of palladium. When you run CODEP, the aluminum goes to the anode. It does not stay in the cathode. And we've actually done something called time of flight spectroscopy at Case Western, looking at a surface as we drill down. And in one of the experiments, we found there was a depletion of aluminum on the surface. You'd expect if you had aluminum, it would go over to the anode. But as we got deeper in, and we're talking about maybe 100 to 200 nanometers, the aluminum content is going up. In other words, it's as if we're producing the aluminum. What we've conjectured is happening in both cases is we're fissioning palladium. And if you're trying to raise money, it's not good to take a noble metal and fission it into base metals.
You're just not supposed to be able to do that?
No, I'm saying it's a loss leader. Hi, I'm going to take your very expensive palladium and turn it into iron, calcium, and aluminum.
So is it unusual? Oh, go
So
ahead.
it's just it's a matter of interpretation again of this experiment.
Well, the data is real. And in fact, in the CODEP, as we found there, we also found that we get volcanoes formed. And I did the calculation one time. The number of neutrons that should have come off doing enough fusion reactions to volatilize, I think it was a 50 micron diameter and assuming about a 25 micron deep hole of palladium, and it's gone. Around the rim, there was aluminum and calcium and iron. We also published a paper where we found that we could change the distribution of the elements by the presence or absence of either external magnetic or electric fields. And so we've published all this data.
And so does this lead then to the application of the technology? Because if you can do this to palladium, can you do this to like radioactive wastes? Can you do this to
Oh,
toxic
that's what Mitsubishi
chemicals?
was doing.
Mm.
Mitsubishi spent a lot of money doing exactly that, and I don't know where that whole effort has gone.
Do these things just kind of disappear because they get swallowed up by various government programs, or like where do they
No,
go?
everyone's after that. The government's hiding all of this stuff. I've been threatened that I'm doing the same thing. That A, I am feeding off the government trough, and B, I'm suppressing knowledge. And no, neither one of those is true.
How have people accused you of that if you're like out there publishing all your results?
You'd wonder because they don't bother to read the papers.
Hmm.
And early on, we worked our way up. We were published in Naturwissenschaften, which is a German scientific journal. It's where the first fission results were published in 1939. So we published, what year was it? I guess it was 75 years later. We published our results of inducing nuclear fusion in a palladium lattice. And I thought this was pretty cool. We're 70 or 75 years to the day after the first fission results. We didn't get much play from that. However, my goal at that point was to go to higher tier journals. So the next paper we did in conjunction with the DOE lab in Santa Barbara, the Special Technologies Lab, was to publish a result comparing DT fusion in the lattice with DT fusion done with the neutron generator using the same diagnostics. And we submitted that to physical review letters, and it took them an ungodly amount of time to reject the paper. And in fact, the reviewers came back and said that we're lucky not to be dead. They had deliberately miscalculated the neutron flux by over 500 times. My colleague Pam said, we should tell them that your hair's turning gray. Maybe they'll publish it then. But the problem was there were 3 reviews. They gave us 2 of the reviews and refused to give us a third. They then told us,
that's pretty unusual, isn't it?
Oh, it's more than unusual. It's an academic crime. They even then went so far as to tell us they weren't giving us the positive review because it would do them no good.
That's great. That's insane.
Yes, it is insane.
This was
Well, as it
physical
turns
review
out,
letters?
yes.
Very
So
strange.
it gets better. So we had a suspicion we knew who the third positive reviewer was because he had specifically asked us as we're writing the paper to cite Buford Price and Cartwright's work using CR39 published in 1979. I said, oh, yeah, Buford, I'm happy to. So we then went to a conference in 2010 up in San Francisco, chemistry conference, and we went over to Berkeley to see Buford. And the first words out of his mouth was, when's your paper coming out? And I said, it's not. They refused to review it. And refused to publish it. We did get it published later that year in the European Journal of Applied Physics. Exactly the same paper. And then 4 years later, Pam and I were so irritated by this that we wrote another paper that talked about the problem of suppression in science. We first submitted it to a journal on essentially scientific ethics that was way out of their wheel well because we're talking about scientific data. Then we submitted it to another one where a guy had written, who was the editor based at the University of Maryland. He had written a paper, a book, and he devoted a chapter to cold fusion, that if you want to get to the bottom of it, you got to allow them to publish the work so it can be reviewed. I submitted it to him. He didn't want to touch it. So we ended up publishing it in the Journal of Condensed Matter Nuclear Science, which unfortunately is the organ of the community. At least we got it out there.
Man, that's kind of depressing. We've covered. It's funny because usually when we hear this kind of stuff, it's coming from people that are, I would say,
well, they probably never got the thing published.
Or they're working firmly on the fringe. One of the things that we do at the project here is we try to talk to people that are well outside of convention, and then we talk to people that are well seated inside of the frame. And it's just really, I've gotten used to hearing this from people that are well on the outside, but it's rough that it's happening even to you.
Yeah, well, it's my colleagues too. We're not alone. I will send you guys a copy of the paper because one of the things that's interesting that I found in writing the paper is the number. Do you know about a book called The Plastic Fantastic?
No.
This is a German PhD who came to Bell Labs. I believe his name is John Schoen, Schoen, And he basically made up data where he was claiming that he had everything from a superconducting material and a whole bunch. He wasted an awful lot of people's lives and time. And the problem was Bell Labs wasn't keeping a good eye on what he was doing, let alone that he was screwing up his results. But worse, Nature, Science, and one of the optics journals just gladly glommed onto his papers. This is like, earth shattering, except it wasn't true. Some 40 papers were retracted once this came out, and his PhD was rescinded.
Wow.
Ominous.
But he had a 10-year run where he did a lot of damage. But I cite that in our paper. Even the big guns, Nature and Science, screw up sometimes. And there are other ones too. Hopping Genes, McClintock,
Mm-hmm.
her work, they refused to publish it.
Yeah, her story is basically just the fact that every time that she tried to talk about it at conferences, they would laugh her out of the room. They were like, this is the
Exactly.
dumbest
Same
thing that I've
thing
ever
with
heard.
plate tectonics. Same thing. Oh, that's impossible.
Yeah. Well, so, okay. This leads us kind of neatly into where we wanted to land the conversation. Did you still have stuff that you wanted to ask? I see you writing over there frantically.
No, I was just trying to draw my way back towards it as well. I mean, I think we've actually kind of talked around lattice confined fusion, but ultimately it was instrumentalizing the findings that were kind of accidents along the way, it seems like. And then you're basically discovering, hey, if we use these metals to create really high fuel densities, we don't need to heat them to incredible temperatures to get these reactions. So,
and we don't have to confine them with great measures. Yeah, exactly.
And so, where is this headed? What are the applications that are immediately going into play?
Well, I've got colleagues in Bristol, England. So they had Tom and Talman, who started Astral Systems, along with Mahmoud, who was a postdoc, or he may have been actually faculty in Japan. He had seen some interesting things using an inertial electrostatic confinement neutron generator. And he had substituted some other metals in there and saw an increase in the flux. So Tom came over and was, I guess, working in his lab. And about a year after we published our PhysRev-C papers, he came across them and understood what was happening in their device. So he called back to his advisor, and his advisor said, "Oh, you got to talk to Talman," who at that point was in Canada, lives in Toronto, still does. And I don't know, 6 months to a year after that, they started Astral Systems. So what they've done is they've basically combined our paper and one of our patents to make a material that they then hit with a deuteron beam inside their neutron generator. And as they put it, increase the neutron flux anywhere from 50 to 100-fold over what you normally would get. He estimates that 99% of their fusion reactions are happening in this near surface. They developed this specifically for medical radioisotope production, and they've sold their first one already in the UK, and they are going to sell a whole bunch more beginning this fall.
So can we explain that to people? So you need to have a source of radiation in these medical enterprises.
No.
Yeah, explain the need for this application.
So when he's got a power supply that accelerates a deuteron beam in an electrostatic confinement device. So nominally there's no target. And so what he's got is deuterons flying around inside this thing at about 20,000 electron volts. They hit a surface inside, which has itself been preloaded with deuterium, and they have a variety of proprietary metals they've put down. And I know how they're doing it because I'm an advisor to them. But the consequence is that this thing produces 50 to 100 times more neutrons than expected. They have a patent which is issued in the UK. It is now awaiting the same travails that we've gone through with our stuff in the European Union and in the US. So,
but what's the final output of those neutrons? Like, why is that desirable for these medical applications? That's kind of what I'm driving.
Well, this thing is only about a meter long and about this big around. It's a very compact neutron source. And it's based in part on work that comes out of Farnsworth, who invented the television. Well, he's the one who invented the electrostatic inertial confinement fusion device, which kids have made for the Westinghouse and Intel awards as part of their science fair projects. It was enhanced by Hirsch in the 70s and 80s, further enhanced by a colleague of mine, George Miley at University of Illinois, and then NSD, with funding from Daimler-Benz, made this a commercial product. I know Talman because 15 years ago on a DOE SBIR at UT Austin, I was going to buy a TT fusion generator because it gives me a flat 1 to 9 MeV neutron spectrum. Unfortunately, we didn't get the phase 2, so we didn't buy it. And not long after that, NSD went out of business.
You said this was going into isotope production for medical
Yes.
applications. So they're using this neutron beam to make these isotopes?
Yeah.
Okay, just trying to close that circuit.
And it's not really a beam, it's irradiating the area around it. So whatever you want to put in there, I imagine you know, technetium-99 is a very popular one. You irradiate moly-99. And the consequence of that is that you then, as they call it, milk the cow. So you can extract it.
How does the cow come into this?
Because moly, M-O.
Scientists.
So is the idea you can generate these isotopes on site then? What's the advantage? Okay.
So this is the beauty of it. Right now, technetium-99, which is probably the most common radioisotope, primarily for diagnosis of various things, you can form a variety of bioactive chemicals that you can stick that onto, and then you can use it as a tracer. So that's great. The problem is that in North America, that was primarily being made up at Chalk River. They closed the reactor down. It was old. It needed to be closed down. DOE put out a huge amount of money to convert the reactor, the trigger reactor at the University of New Mexico, at the University of Missouri, to convert it from highly enriched uranium to lower enriched uranium because they were making the isotope. But then the question is, are you making as much as you'd like? Probably not. And the UK has no way of making this now. So this is in short supply. But the major thing is, if you have the ability, and again, one of the fluorine isotopes, I think it's 18, comes into play. There are isotopes that would normally be made in a nuclear reactor. But if the reactor is more than a few half-lives away, you can't make them. So there are people building huge, expensive
cyclotrons. Like in terms of
cyclotrons.
transport time.
Exactly. And so people are building cyclotrons around the world to do this. I've worked with one of the companies, IBA, in Belgium, that's one of their marketing things. But if you could put one of these little neutron generators in every hospital on the planet, you got a whole wealth of radioisotopes made right there.
I see. That's really cool.
Yep.
What
So
about
I like it.
Yeah, I mean, so what about lattice confinement fusion as an actual power source?
Well, we've published papers on our ability to fission uranium-238 and thorium-232. So we are in the process of scaling that up with National Science Foundation funding in conjunction with the work we're doing at NASA as a way to melt through the 25 mile thick icy crust of Europa and Enceladus to get to the ocean underneath.
But what about more prosaic domestic production of energy using fusion? Is that just still a total pipe dream?
There's a lot of things that you both have, and you primarily have lit on. You know, what is the reaction going on here? What is the reaction that essentially changes the fusion reaction products from being near parity to basically going way towards tritium? That has the possibility, if people put enough money into it, to become potentially a neutronless fusion source for energy. There's another one that you may have heard of. It's the PB. You know about that? Proton boron. So if you take boron 11 and you add a proton to it, you get carbon 12. It is an aneutronic fusion reaction. That's the good news. The bad news is if you do this conventionally, that reaction has a peak at 600 keV. So multiply that by 11,000, you're talking about billions of degrees. So if you thought it was hard confining something 100 times cooler, you ain't seen nothing yet. But the second problem, which is a bigger one, and Todd Ryder, for his master's thesis at MIT in '99, pointed this out very nicely. When you get hotter and hotter, you get any contaminants into the plasma, which will happen. They will, as a function of temperature, and I think it's a T to the 4 relationship, they will radiate X-rays and cool your plasma off. So you will have a devil's time getting it hot enough. Now, we do have some evidence that this has been done in low-energy nuclear reactions. It's not been recognized as such, but I suspect that that was what was happening. There's papers published out of the Naval Research Lab where they use boron, 5 to 10% boron in a palladium lattice. Their thought was this was good because it removed oxygen from within the foil as it's melted, as they're making it, and it becomes a dross on the top and you can get it out. But what happens is, when I learned about this initially, they were using basically natural abundance, which is I think 20% boron 10, 80% boron 11, and these particular cathodes that the Naval Research Lab had gave excess heat. Well, they attributed it because they had removed the oxygen contamination. I suspected, but have never had a chance to follow up on this because I knew both of the people on it. It was Imam and who was the other one? Anyway, 2 physicists there, or 2 metallurgists there, that they may have actually introduced inadvertently the proton boron 10, because the way in which they loaded it, whether it's from deuterium gas or electrolytically, you've always got protium. You've always got protons in either the gas or in the water. So that's another one of these things to track down.
So I guess something that is still missing from my mental image of lattice confined fusion, and maybe you have a sense of this, like what is the ideal case in which we can use it as a power source? Like not where you're irradiating uranium-238 or on Enceladus or whichever uranium it was, 235? Sorry, I can't keep track of these things. But so where it's just purely a renewable fuel source that doesn't require the use of these really nasty radioactive substances. Is there like a big picture of this that
Well, here's the good news about the uranium one. First of all, uranium-238 is not all that nasty. I mean, we're surrounded by it on the planet. So is thorium. There's 3 times more of that. The second thing is that the initial work we did showed that we don't fission it the way everybody else does. We actually end up basically with dirt. We end up with aluminum, calcium, the same things that we did when, let me put it a little differently. Nobody really knows what the energy required to fission palladium. It's in the middle of the periodic table. It holds on to its guts very happily. Arguably, it would take a particle, a gamma ray, or maybe a proton beam or a neutron beam that's over 50 million electron volts to shatter it. Most likely what will happen is you'll knock something out. You'll knock out a proton, an alpha particle, or a neutron. We have clearly fissioned it into stable things. The initial work we've done with the uranium-238 indicates the same thing. We're getting out stuff that shouldn't be there, not from a fission perspective. So that's a good thing. And it also says that, my goal is to burn up spent fuel rods, get paid twice. You give them to me, you pay me for taking them, and then I get somebody else to pay me to make electricity from them. And I wouldn't dispense this so fast because you get 10 times more energy out of a fission reaction than you do out of a fusion reaction. So coupling the 2 of them together is an old idea. It actually goes back to Hans Bethe, who suggested this back in the late 70s. But a number of cockamamie schemes like lining the inside of NIF with spent fuel rods seems like a really bad idea. That was
did
called
you say
light.
you get 10 times more out of fission than out of fusion?
Yes.
I see. I thought that was the
You get
opposite of what we started with the
you get
bombs.
you get you get 24 MeV out of both channels from fusion. You get about that's 190 MeV out of one fission. Combine the two of them together, and you got over 200 MeV.
And so basically the future of lattice confinement or low energy nuclear reactions, you think isn't using them as the power source. You think that it's linking them
There's
into the systems that already exist in order to be able to accomplish something that has a dual utility.
If you stage things, the first one you'll be able to go after is one that already fits into a scheme that's already there, and in fact make it cleaner or better or something. The second one would be given enough money from that you can get down to the bottom of why this worked in the first place, and then go for something that is completely aneutronic and just gives you energy. Now, whether we can actually do that technologically remains to be seen. Scientifically, as far as I'm concerned, it's been demonstrated. Can you technologically use it? I don't know, because technology means, can you scale it and will it last long enough to be useful?
And so what's do you have
I think that's a really, really good point to, and a really good set of questions to go into any of these conversations with these people who are promoting their futuristic fusion devices.
Yeah, absolutely.
I've been asked to evaluate probably, I don't know, 6 to 10 devices over the last 20 years. And most of them have been cockamamie. A few of them have shown promise but don't scale.
Mm.
And I'm very curious across a whole bunch of different ways of driving them. What is it that keeps them from scaling? I find this a really fascinating question. And to me, it's a deep question whose answer tells us what's really going on.
And
That's really
that's sort of the
fascinating.
new scientific understanding that needs to happen. Yeah.
Yeah, and I don't believe there's any need for any new physics to make this work. I've got colleagues that say, "Oh, you're somehow exciting the gluon plasma inside of quarks." No, I don't think so. I mean, the energy scales are wrong, the time scales are wrong, and your idea is wrong.
I appreciate that. I think that there's a lot of mysticism that gets put into into this space, especially because I think that there is pieces that still haven't been fully articulated inside of the models. And so I guess the one last thing that I really do want to understand is that in a pure 100% sci-fi universe where we're able to get fusion power that is completely derived from these neutronless fusion reactions. What does that actually look like? Is there any kind of thing that people are aiming for that's theoretically been proposed? Or is it just the same place that we end up at with nuclear uh, fission, which is that you're boiling water and driving a steam generator?
Yeah, I'm actually a real proponent of magnetohydrodynamics as a way to convert charged particles to power directly.
Mm,
My colleague Teresa Benio at NASA, she did her PhD thesis on that, and I keep reminding her of that as we go forward.
interesting. Okay, well we'll have to pick that up next time because I think that
I think
opens in
one of the
another can of
things you should
worms.
pass on to your other interviewees is just remind them of, I believe it was Fermi's comment. Your idea is crazy, but not crazy enough to be true.
Hmm.
And I may have misattributed it to Fermi. It may actually, it wasn't Szilard. I'm trying to think who else it would have been in that time frame. At any rate, that'll do until I figure out where the quote came from.
Excellent.
Well, I think
It's
I
not
think it's a
mine.
really interesting frame that like these processes have been demonstrated, to different differing degrees of success, and the question really becomes what's the plan to scale them, and how
Yep.
realistic is that? I think that's a really good place to head into these conversations.
Absolutely.
Well, let's put it this way. I have filed a patent disclosure with NASA on the underlying process using uranium.
What does that
And
mean? I'm unfamiliar with patent law.
fusion fast fission of uranium.
But patent
It took-
disclosure meaning that you get to share the patent, or?
no, it means that, well, it's based on the work we published in 2020, and it took me 5 years to figure out how to apply it usefully.
Basically, they won't grant you a patent unless it's a feasible construction. And so,
So patent disclosure is the process by which NASA grants you the right to patent something? Like,
No, NASA then files a patent, and if they don't, I'll file it.
I see.
but it's sound on paper.
Sound on paper. All right, excellent. And so 5 more years
Well,
from now, you'll
the
be
other
turning
thing is
uranium into dirt?
basically,
That's
yeah.
pretty awesome.
The patent doesn't go into that part. It just goes into how the process works. And it may have additional applicability to stellar formation in protodisks,
Mm,
I love it.
which I like.
that's excellent.
But the main thing is to patent its application, which that's mine, not NASA's.
That's really cool. I mean, I look forward to seeing how it all unfolds. I feel like we're at the crux of something really, really interesting. It took us so long to be able to talk to you. I think Shiloh's been emailing for at least a year, maybe
Oh, you're
2.
kidding!
Oh, more than that. Yeah, there's only a couple of lattice confinement papers in existence on the internet that I could even find under that name.
Well, you've got my two, right?
I do, yeah, but I think I emailed almost everybody on all of those papers, and oftentimes the different scientists would write back and be interested in talking, and then there would be some administrative problem, and
Yeah,
We have a problem with the PAO. It's not a problem. The PAO is trying to protect us and
Yeah.
protect NASA.
yeah, I get it.
And
I get it.
and I didn't even learn about you guys until probably a month and a half ago.
that's
And I was put under a lot of pressure. You really need to talk to them.
Oh, well, that's good. I wonder where that pressure came from.
Thanks, NASA.
Yeah.
But yeah, it's been a real
There's
pleasure.
there's someone you really need to talk to, and I don't know if you know the name Sonny White.
Mm-mm.
Okay,
I
I
don't
will
remember.
send you Sonny's contact information.
That'd be awesome.
Sonny is not working in this sphere
Okay.
yet. He knows of. Keyword. But what he has done, based on work he's done he was with NASA for about 20 years. And he had what was called Eagle Works. He then started I think it was called the Limited Space Foundation. We funded groups doing things.
The real world is calling.
Yeah, the real world. Well, that's my other group that I work with. They can wait a few minutes. But the point is, Sonny has gotten NSF and other support to build Casimir cavity batteries. And if you're familiar with Casimir forces, it's 0-point energy related. They are not the same. Sonny will go to great lengths explaining why. He's extraordinarily personable. He was even on Joe Rogan at one point, which just blew me away. I don't know why Joe cared, but at any rate.
0-point energy is very hot.
Exactly. And I should tell you, I know this well because I'm also an investor in this company. So I'm hedging my bets.
Sounds really cool. Yeah, I'd love to talk to him.
Yeah, absolutely.
Okay, so I will send you guys Sonny White's contact information. And I think he's good to talk.
That sounds fantastic. Yeah, and I really appreciate you taking the time. I know you got a lot of stuff on your plate, and I know that 3 hours.
Yeah, well, apparently a piece of it just came over the phone.
Yeah, exactly. But
I did want to ask you, do you know who Jean-Paul Barbarian is?
you've mentioned him. I wrote the name down, but I don't know.
Okay, I will get you I know Jean-Paul very well.
Excellent.
And another one is Edmund Storms.
See, we're like total neophytes in this.
That's all right. These guys will give you very interesting views, and you can triangulate on the truth. And you'll find out nothing I've said makes any sense.
Do you think that Pam would talk to us?
That's a good question. I will ask her.
All right.
This is how we always get the best guests, is friends
Yeah,
and friends.
no, I'll first thing I'll do is I will ask each of them if they would mind.
Yes.
Okay, out of courtesy to them, so they're not blindsided. And then I'll get back to you. It'll probably be early next week, only because I'm not sure I can reach some of them as easily as I'd like.
Well, if you want to wait till the podcast comes out so you can share with them what they're getting
No, I'm
into.
not worried
Okay,
about that. I'm
okay,
hoping to take some of the heat off of me.
okay. Yeah, I mean, the more voices in something this complex, the better, honestly. That's why we're always trying to triangulate these perspectives.
Jean-Paul and Edmund and Pam have all worked in this space. Edmund is retired. We're co-writing a paper with him and one of my other. Oh, I know who you should talk to.
This is awesome.
Yeah, I mean, like,
Lou.
we're really, really interested in trying to understand the underlying processes that are happening here. Like these questions that we were asking you about it, like, okay, well, how does electron screening actually like work? What's happening?
Oh, then
These,
you need to talk. You need to talk to Konrad Zerski.
all right,
He's in Poland.
all right.
Lou DiCero is with the U.S. Navy Surface Warfare Center. Pam is
That's
retired
going to be
from
a hard
Space
interview
War.
to get.
Lou has been remarkably prolific in talking about what he's doing. And I reminded him actually just yesterday that we need to take some steps so he doesn't get in trouble with his management.
We never
Because-
get people in trouble. We're very careful.
No, that's not the point. Just talking to you could get him in trouble.
I can imagine that it's a delicate subject.
Yeah. Jean-Paul is a retired professor in Marseille, France. Ed is retired from Los Alamos and more or less retired from the field now, but we're still doing a paper with him. Pam is retired from U.S. Navy Space War it's been 10 years now, but she's been working with me that entire time since. And we worked together. Oh, good Lord. I mean, I made their acquaintance back in 1994, I think.
Ancient history.
So I've been
at this point.
affiliated with them, and then we began working closely about 10 years later.
I mean, it's a super cool space. I have a model of the world, which is that we really only start to understand things when we build something on the basis of some phenomenon. And the
Yeah.
fact that the way that you've been talking for this entire conversation just suggests to me that there's something that's not, like, there isn't a mental model yet of some of these processes. And it would,
Not a complete model.
that's what I mean. Like, because for me,
Right.
like, the way that I think is I need to be able to have a movie of the thing that's happening in my head so that I
Yeah.
can really think about it. And there's pieces here where like things come from the origin point and they get to some weird fuzzy place and then they emerge on the other side. And I'm really driven to understand what is in that fuzzy place. And it's so
Well,
cool.
you're in the same place I am.
Excellent. Okay.
Because I started this by saying this is impossible. And then I did it, and I said, oh my God, now what am I going to do?
Well,
It's a
hopefully,
good position to be in, I suppose. as a
Yeah.
Yeah, and that
scientist.
was over 30 years ago.
yeah, well, sometimes these things take time, I suppose.
I should leave you one passing thought, too. During the 90s, I stopped publishing
Hmm.
because I was involved with what was then called the cold fusion field. I was involved with acoustic fusion, and I was involved actually 4 fields: magnetic fusion and laser fusion. And I didn't dare let any of these other groups knew that I was working in the other groups. I would have been cast out.
That's
I would have joined the
wild.
poets at the bottom level of hell.
It's so funny how these social hierarchies are born, even inside of these places that are supposed to be, you know,
Objective
Well,
towers of
pure of
truth.
when you
heart.
talk to some boss, she will tell you scientists are people too.
Hard to remember sometimes.
We've come to realize this.
Yes, indeed.
Well, this has been a real pleasure. This was, more fun than I thought it would be. But I am very serious. Please send me on any link to that star.
Ah.
Okay. And the fact that it's got gamma rays, was it picked up by the Fermi telescope?
Oh, I don't know about the gamma rays. That
Actually,
was a different issue. I just know that it had these extremely heavy, short-lived elements that they were having trouble making sense of. But it was called Shabilsky's star. I can send you.
Yeah.
I can at least send you the Wikipedia page.
Yeah, the gamma rays was just an off the top of my head thought where I was wondering if it was possible to derive the theoretical reactions happening inside of a star on the basis of the radiation that you would expect.
Well, the problem is all the action usually is deep in the star, and the gamma rays you're going to see out have had to pass through an awful lot of, shall we say, moderators that are going to change what's coming off. So you're really seeing what's happening at the surface in terms of gamma interactions. And the same thing is true for everything else. My main interest in James Webb is I can look at things that are stellar envelopes up close and personal, if you will. And because the spectroscopy is spectacular, I can see through the dust and I can see lines that show me things that maybe shouldn't be there.
That's really wild. I look forward to seeing where you go with that. We should talk again.
Yeah, we'll be in touch.
Yeah, we'll let you know when we're in San
Take
Diego.
care.
Thank you so much.
And
Larry.
I'll remember Christmas. I should be in San Diego, which, to tell you the truth, is a lot better than spending it in Siberia.
Is that where you normally go?
Siberia?
Yeah.
Not anymore. I haven't been back to Russia since 1991.
Но вы говорите по-русски, вы правильно сказали Новосибирск.
Oh my God! Очень хорошо.
I noticed you said Novosibirsk, and I was like, that guy speaks Russian. Because normally
I used to a long time ago.
That's really funny.
Yeah, I enjoyed it. Actually, I was also learning Arabic because I was working in the Middle East. I really wanted to read The Prophet in the original. Not the translation.
You're not dodging those CIA allegations very well at this point. Arabic, Russian, international travel.
What allegations?
The
I had
suppression of the truth allegations.
Yeah, exactly.
I had to give up my clearances because I was not interested in telling them everything I was doing, which was not government sanctioned.
Amazing.
And I'll also add, I've never killed anybody intentionally.
I don't like that asterisk very
there's
much.
been a lot of dead bodies in the story that unfolded today.
There have.
But I'm sure it was totally natural.
We're gonna start making sure we lock our windows.
This is what you get for talking to me. You could come to a bad end.
Well, it is what it is.
You heard it here first, folks.
It really has been a pleasure. But I'm quite serious. I would be happy to work an astrophysics paper if you guys, either of you, could pull something in that would add to it. I think that would be very exciting.
That'd be awesome.
All right, we'll put our heads to it. Yeah.
At the very least, you might say there's nothing there. That's a paper in its own right. Stop going down that rat hole. Ciao.
We got ideas.
Thanks,
All right,
Larry.
we'll talk to you again, Larry.
See ya.
Bye.
Bye-bye.